So welcome back, everybody. So to this afternoon session, so European time at least. So we have, first of all, three young and junior speakers. The first one will be Michele Dolce from Imperial College in London, and is going to speak about long-time behavior in the 2D Euler-Boussinesq system near established stratified Couette flow.
Yeah.
So,
but yeah, I would like to first thank Gianluca for the nice introduction and the organizers for inviting me here at this very nice conference, which I would have loved to attend in person. And so let me start with this is the outline of the talk, and I want to start with a very brief introduction of what actually is the system that we are going to describe today. So the 2D Euler-Boussinesq system are nothing more than inhomogeneous and incompressible Euler equations where you do assume that the density multiplying the acceleration of your fluid is actually constant, so that basically the main effect of the density comes from the buoyancy forces. And this approximation was done by Euler-Boussinesq in 1903, and it's clearly mathematically convenient because now you can divide by this constant here that should be here, basically. The domain we are going to consider today is T cross R, which is an infinite periodic strip, or you can think of it like as a cylinder with infinite extent. And we want to consider a particular equilibrium, which is the following: a linear shear flow, so a velocity field, which is called the Couette flow. And then we consider a linear stratification, and this you should think more as a physical sort of approximation of e to the minus by in some sense. But what is important of this stratification is that it is stable. What does this mean? That the heavier fluid is at the bottom and the lighter one is at the top. And this is a situation that we observe, for example, in the ocean, where the hotter fluid is on top of the colder one. And of course, there is also an associated pressure. Now, we do want to perturb around the stationary state, since you are considering the Boussinesq system, it's convenient to introduce the vorticity, and the flow is 2D, and a scale density. Here, when you talk about stratified fluids, there is a very important parameter which is called the Brun-Väisälä frequency. This parameter somehow measures how much your fluid is stratified. Writing down the equation for the perturbation, they take this form, where you see that there is a common transport term, so density and vorticity are vectored by the background flow. There is a linear term that couples the equations, and the fact that here you do have constants simply come from the particular solution you chose, and the nonlinearity. As usual, the velocity field is recovered through the standard Biot-Savart law in 2D. Now, our goal is try to understand what is the long-time behavior of the vorticity and the density. The first things we want to do is see what happens at the linearized level. And I quickly recall what is known in the homogeneous case, where the equations reduce to this simple transport equation that we can solve explicitly. And in particular, since we have also this particular domain, we can represent the solution in two ways, either in the physical space or in the Fourier space, where we gain some insight. That is, the information is traveling to high frequencies in the vertical direction. What does this mean? Well, if you consider, for example, this particular initial datum, just taken mean zero for convenience, you see that first the shear is stretching our perturbation, and due to the periodicity in the horizontal variable, it will wrap around the torus, and you will see the formation of stripes, which are thinner and thinner. And therefore, you can think that you are creating high gradients in the vertical direction, namely large frequencies, or equivalently, small spatial scales in the vertical direction. And when you do have oscillations, you should expect to observe some sort of weak convergence to zero, for instance. And this is basically the main thing you can understand by looking, for example, at the stream function, which is related to negative Sobolev norms of the vorticity, of course. And as we saw in the previous talk, a way of measuring mixing is through negative Sobolev norms. And in this case, the computation can be made explicitly, and we obtain that indeed the stream function is decaying even mode by mode. If the k is not zero, k equals zero is the x average, which is just conserved by this for this dynamics. But what is really important is that you are paying two derivatives to actually get a power of t squared here. And this is an essential feature. You always lose derivatives if you want to get some decay in negatives over norms. Now, since we are talking about fluids, we are actually interested to what happened to the velocity field, which is nothing more than the orthogonal gradient of the stream function. And upon removing the k equal to 0 mode, which in this case is simply a shear flow due to the incompressibility condition, what you actually have is that the velocity field is decaying to 0, again, upon paying some derivative on the initial vorticity. And this is called Inviscid damping, because somehow is a damping that happens even in absence of viscosity. But what is the physical meaning of this result is that if you do perturb a shear flow, on the very long time, you are going to converge to another shear flow determined by the background Couette plus the x average of your perturbation. Now, this mechanism was essentially already understood by Kelvin Orr in 1907, and later classical investigation has been done for other shear flows. But to actually promote this linear analysis, this kind of convergence to the nonlinear case, it took us more than 100 years, and there was a huge breakthrough made by Bedrosian and Masbouli in 2013, which I'm going to discuss more precisely later on. If you want to consider instead more general shear flows instead of the simple Couette, the problem becomes very involved, complicated, and K is predicted that the analogous Inviscid damping should hold, but it took us 50 years more or less to prove that this is the case. And today, I think those papers by Wei, Zhang, and Zhao contain the largest class of shear flows for which we do know Inviscid damping. Now, instead, let us move on and see what we do actually have for the Boussinesq system. And so I want to first show you some numerical simulation. In this particular case, where I just want to perturb the density and assume that there is 0 velocity field, so 0 vorticity. And here I'm just putting 2 blobs of density, right? So this is positive and this is negative. First of all, I want to consider a case where we do know that there are no unstable eigenvalues. And to do so, there is a very well-known criterion for stratified fluid, which is called the Miles-Howard criterion, which is telling you that if the Richardson number, that is this quantity here, is greater than 1/4, then you do not have unstable eigenvalues. Now, for the Couette flow being u prime equal 1, the Richardson number is simply the Brunt-Väisälä frequency, and therefore we are going to consider always this restriction here on the Brunt-Väisälä frequency. Now, if you run your numerical simulation like time point 1, basically the shear flow has no influence in the sense that just tilted a bit our perturbation. But what is interesting is you are creating some vorticity, right? Because you can think of this term as a source term. So vorticity is being created even if you start with 0 velocity. And somehow here there is the plot of the velocity field that shows you how the fluid tries to restore what it thinks should be the equilibrium state. And then if you run somehow those are like 2 rods of vorticity, okay? Now, if you run the numerical simulation long enough, you will clearly observe the formation of stripes, and therefore information is again sent to high frequencies in the vertical direction. And this is mainly because of the common transport term, which is here. But then what is more interesting, and I would like to stress, is that indeed the L2 norm of the velocity field of the vorticity, sorry, the L2 norm of the vorticity is actually growing. And this kind of resembles a square root of t as a time dependence. And you also observe that actually the density is decaying. So this is not purely a forcing term. There is some mechanism going on. And now here you cannot see maybe I can zoom in, yeah. You see that the velocity field, what it's doing is actually first growing and then it decays. Now, how to quantify mathematically what we observe at the numerical level? Since, again, we consider this particular domain T cross R, it is convenient to do Fourier analysis, which is the thing we are able to do in the homogeneous case, for instance. And therefore, we perform a change of coordinates first to follow the characteristics of the system determined by the background flow. And we are going to denote from now on with capital letters variables in the moving frame. The differential operators are going to change in this moving frame, and therefore you will see time dependence. Somehow also the differential operators are tilted. And there is a symbol associated to minus the Laplacian, which is what we call P, and it's going to appear several times from now on. Now, it is more convenient to actually rewrite the system in terms of the horizontal derivative of the density, because so that here you have actually a real operator, a real Fourier multiplier. And this is the system you observe. Now, first thing to notice is that this is a 2D non-autonomous dynamical system, because here you do have a time dependence in the denominator, and it sort of have a wave-like structure, I would say, even though you know, these coefficients have not the same modulus. So, and clearly you cannot solve this system by means of simple formulas, because here you have a time dependence. Now, but here it comes one of the main ideas that I want to show you today, that is the so-called what we call symmetrization scheme. That is, try to weight your vorticity and density perturbation with some Fourier multiplier in order to symmetrize the system. What do I mean by this? Like, rewrite the system in this form. And what are the features of this formulation? Well, the trace of this metric is 0, as we had in the previous case, of course. But now notice that the anti-diagonal terms, they have opposite sign, but the leading order term is exactly the same. Now, you know, they are opposite in sign, but the modulus is the same. Sorry. Now, how can you actually guess why exactly this power here with this exponent? Well, if you for a moment think of P as being just T squared, here I'm trying to control a quantity which is like omega over square root of T, and this theta multiplied by square root of T. If we now, for example, are able to prove that those quantities here are of order 1, then I'm showing that omega is square root of T, and theta decays like 1 over square root of T. How to prove this, this kind of bounds, which I just told you? Well, what you can do is try to perform an energy estimate. Therefore, you introduce an energy functional, which is this one, and shouldn't be really surprising in the sense that it is exactly the conserved Lyapunov functional you have if A and B were constant. But there is a nice feature that is this energy function is coercive if you satisfy the Meltz-Howard criteria. So somehow we are in this kind of sharp, this method to recover what is known from a classical spectral analysis. And then you know, again, it is not conserved. So you perform some Growart type estimate and you bound from above and below this energy function. And this is kind of telling you that actually, if you think of ZQ in the Z and Q plane, these are evolving like in an ellipse, and meaning that you can bound in an annular region this quantity, telling that Z and Q basically are of order 1. And as I was trying to explain you before, sort of heuristically, once you have bounds at Z and Q, you can recover information of the vorticity and the density. This is the main content of our theorem with Roberta Bianchini and Michele Dolce 2 years ago. And here I'm introducing this notation like FNEC, which is like F minus the X average. And the theorem goes as follows. It's telling you that the X derivative of the density and the velocity field experience Inviscid damping. Namely, you do have a decay upon always paying regularity, but notice that the decay is lower compared to the homogeneous case. And this is essentially caused by the fact that now the vorticity and the gradient of the density are growing like square root of T. And this is what we call shear buoyancy stability. Why not only the vorticity is growing? Because you should think that the system is like a wave, it has a wave structure. So at some point, the vorticity might even become 0. Right? So in some sense, you need to include the case where this quantity goes to 0, but there is some other quantity which is growing, that is the gradient of the density. But notice that the density is more stable with respect to a pure transport because its L2 norm is decaying. And indeed also the gradient is growing slower. Now, for the Couette flow, we were not the first to prove the upper bounds, which were indeed already known by Hartmann in the 75. And you can sort of approximate the system with hypergeometric functions. And Yang and Lin made this procedure fully rigorous from a mathematical point of view. And they recover also the upper bounds. And they can also go beyond the miles-over criterion. This is kind of interesting. But what for us, what was more important, it was actually to prove that the same holds without the Boussinesq approximation and for shear near Couette upon some small correction. Here I would like to mention that actually the symmetrization scheme, which I discussed in the previous slide, was introduced by Paolo Antonelli, myself, and Pierangelo Marcati in the same year to study the stability of the Couette flow into the compressible fluid, where we can handle also the case with viscosity. Now, once we have, I would say, sort of understood what's going on at the realized level, let us move on to the nonlinear problem. In this slide, I'm trying to show you what happens in the homogeneous case. Now, first of all, since the velocity field is divergence free, it is convenient to rewrite this operator in this way, where you do isolate the shear flow component of your velocity field plus the non-zero x frequency. And now you do observe that this is the system that you get, but now the profile, the shear flow profile is determined by the solution itself, so it is nonlinear, and you have a nonlinear Foxing term. To see what happens, here I'm showing you a nice numerical simulation done by Schnirelmann in 2013, where what is he doing? Well, he just plays a blob of vorticity, and there is a background Couette flow, and he let the system evolve. And on a sort of short time scale, you basically observe just the linearized dynamics, namely this formation of stripes, and information is sent to high frequencies in the vertical direction. But if you wait long enough, you will observe what is called an ego, namely a sort of an unshearing mechanism that tries to form a large scale structure. This is also known as a high to low frequency cascade that in 2D Euler equations can happen essentially because you do have the conservation of the energy, but also of the entropy. And so you cannot just send all the information to high frequencies, otherwise you would violate the conservation of the energy. And therefore, how to try to quantify this high to low frequency cascades, which, by the way, I forgot to say, but was already observed by Van Nest in 1998, but somehow with not these nice pictures. Now, let's try to understand this cascading mechanism. How to do that? We need to first think of a toy model to see what is actually happening. And this is a purely nonlinear effect. Therefore, we want to understand what this term is doing in the equation. And as an oversimplification, I'm assuming that the zero frequency, I will just ignore this term. And I do the change of coordinate dictated by the Couette flow. And first of all, there is this nice feature that once you change coordinates, these gradients here do not have a time dependence, as you should, as one might expect in principle. And this is essentially related to the Hamiltonian structure of the system and the fact that this is like a standard change of coordinates. And now you want to rewrite the term here on the Fourier space, and I want to understand just what is doing, just what are doing the V derivatives, because we know that we are creating large frequencies in the vertical direction. Therefore, I claim that this is indeed what the worst possible term that is coming from the nonlinearity. Now, if you just look at this red term, I don't want to investigate at this level just the full nonlinearity, but just look at the red term. Now, the red term, you can write down the Fourier transform of this guy, and it takes this form. Notice that when t is eta over k, which is called critical time, you will see a factor eta over k squared. Now, in principle, eta over k squared can be extremely large, and you should expect to be large because you're sending information to high frequencies. And therefore, you can think that you are there is like a growing mechanism for the factor omega k that can be amplified by this number here. And this is called the OR mechanism, because already OR in 1907 understood that this could potentially create a lot of trouble. Now, what is the worst possible case scenario? That this growth is actually transferred to the k-1 mode. So we are trying to see an unshearing mechanism. Therefore, we want to see how information is sent to low frequencies in the horizontal direction to sort of revert the background shear flow in some sense. Therefore, the cascading mechanism is a high to low cascade that we want to investigate. And if you imagine that now this growth, worst case scenario, they accumulate, what you're going to observe by standard Thilling approximation, it is indeed a loss of exponential amount of derivative, which is called also Gevrey regularity loss, that can be extremely large and potentially unshear your profile. Now, what I tried to explain in just one slide, the mechanism is way more complicated, but somehow the huge breakthrough of Bedrosian and Masmoudi in 2013 was to make this picture rigorous, and they were able indeed to prove that the asymptotic stability of the vorticity in Gevrey 2, and then Masmoudi actually proved that basically Gevrey 2 is sharp for the asymptotic stability in the sense that basically they were constructing an eco, and then UNESCO and Gia were able in 2019 to remove the infinite extent in the vertical direction and consider just a finite channel. What other examples do we have? Well, we do know the point vortex, again by UNESCO and Gia in 2020, which kind of shared some similarities with the Couette flow in terms of the main mechanisms that are in the system. And then again, UNESCO and Gia and Masmoudi and Zhao were able to prove for a large class of strictly monotone shear flows, where now there is the linear term, which is problematic and cannot be treated perturbatively. And indeed, they had to introduce new ideas and powerful ideas to solve basically the same problem in two different ways. And they did essentially at the same time. And these basically are all the examples we know where we do have nonlinear Inviscid damping. And in some case, which I'm not going in, to explain what it is, but in some case, there can be obstruction to a convergence towards a shear flow. What is known instead for the 2D Boussinesq equation? Well, without a shear, there is a huge literature, and here just mentioning a few names, and I'm sorry because I'm definitely missing someone. And instead, if we consider shear flows in 2020, Zillinger, Deng, Hu, and Zhang, they do prove the stability if you consider viscous and diffusive Couette. What do I mean? You do have the Navier-Stokes equation, and you think the density as the temperature so that you can include also a viscosity coefficient there. And in this case, you can even remain in turbulent spaces. And on the other hand, if you remove the viscosity and the density, but you keep the Navier-Stokes equation, Masmoudi, Saiduari, and Zhao proved a nonlinear stability result, and quite surprisingly, in an infinite regularity class, which is larger than this one. And there are reasons why we expect this to actually be sharp. And for the Inviscid problem, instead there were, at least to our knowledge, no results. And before presenting the main theorem, I want to just show you what are the main, I want to give you some preliminary observation, what you should expect in the system. Well, consider now a perturbation of size epsilon. The zero mode is not conserved and there is no decay mechanism. So if you want to do a perturbative analysis, at most you can arrive on this time scale if you're lucky enough. Otherwise, you need to consider a nonlinear change of coordinates, that is, follow the shear flow determined by the solution itself. So I like to say that this is a mixed Eulerian and Lagrangian point of view, because we are following not the entire flow, but just what you think is going to be the most important part. And this was, of course, done also in the homogeneous case, and it is crucial to do this change of coordinates if you want to actually prove the asymptotic stability. For the UNEC, we definitely have at least the Eagles stabilities, but we may hope for some decay from the Inviscid damping. And for the Boussinesq system, we also have the instability coming from the linearized behavior. And therefore, since they are going like square root of t, on a time scale epsilon minus 2, our perturbation can become of size 1. And therefore, we are out of a perturbability relation. And now I claim that indeed the linearized behavior persists up to a time epsilon minus 2. And the actual statement of this claim is the following. I'm sorry, it is a bit technical, the theorem, but I've tried to explain what it's saying. So you do have an initial perturbation small enough in a Gevrey space, which is identified in this way in Fourier space. Then on this time scale, you're able to control the X average. in the sense that you can undo your change of coordinates, and this is crucial. The vorticity and x derivative of the density along the nonlinear profile, because it's determined by the solution itself, satisfy this estimate. And you do have the Inviscid damping we observed at the linear level for the x derivative of the density and the velocity. What is important is that we are actually able to propagate also the growth of the vorticity and the gradient of the density upon assuming some non-degeneracy condition on the initial data. So this was, to our knowledge, the first result doing this kind of long-time behavioral analysis in around the shear flow in the Inviscid case. And here is why I say the linearized behavior is observed also at the nonlinear level. Now, in this very last few minutes I have, let me give you a very hand-waving sketch of the proof. What is, first of all, since we know how to do the linear problem, let's try to apply what we can do at the linear level in the nonlinear case. So we do perform a symmetrization scheme, but now we do have nonlinear errors. The goal is to prove that actually Z and Q are uniformly bounded by this epsilon. But if you just try to do so, it won't work. There are regularity losses and so on. There is this blue term, which I say is subtle because it's essentially coming from the fact that you are doing the symmetrization scheme based on the linear change of coordinates, but in reality, you're doing the nonlinear change of coordinates. But luckily enough, you do have an upper bound of this form for the blue term, and when integrated in time on our time scale, we are able to control it. The red terms being essentially red there, it's clearly dangerous because it's the one creating the Egos instabilities, plus there may be even something worse. And now the idea is like to construct a toy model to build a weight, which is a Fourier multiplier in our case, to weaken the norms. This idea of weakening the norms goes all the way back to Nirenberg to prove Cauchy-Kovalevskaya type theorem, but actually the design of the weight is probably the most innovative part for this work. And then the idea is like, okay, try to do energy estimates, because a fundamental feature of the linearized problem was that we were able to do energy estimates. And in a bootstrap scheme, at this time scale, the weight must have this property that is kind of telling you that you are introducing an artificial damping in the equation. And the energy function you're going to get are like the linear energy functional, exactly the one we have at the linearized level, but now summed over all frequencies. And the goal is to bound this as epsilon square. But if you try to do so, it won't be enough to control just this energy function. You actually need a control also on the vorticity and the gradient of the density. And therefore, you introduce what we call the natural nonlinear energy. Why natural? Because just by looking at the Boussinesq equation, it will be the first energy estimate you will try. And now we need to allow this energy to grow, because the vorticity, this quantity is actually growing. And therefore, the bounds that we want to propagate are the following. And this energy function is at the highest level of regularity. But then, of course, you do also have to control the coordinate change. I'm just hiding you what it is, because it's kind of awful, its expression. But the idea is you need to allow also the coordinate change to grow. This is just a sketch of the weight, somehow telling you how you have to construct, in the sense that you should observe that the weights are unbalanced on frequency. They do change depending on where time is with respect to frequencies. So are really anisotropic weights. And now I just conclude my talk with this slide, and I thank you for your attention.
Thank you very much, Michele. And we can start at question time. So is there any questions or comments or remarks?
Hi, Michele, very nice talk. I have a quick question. So I, of course, understand you're using the structure of the shear flow in a fundamental way here. But I was wondering, I always wonder whether the result of Bedrosian and collaborators, where you have scalar mixing, but the velocity comes from Navier-Stokes forced in a certain way, could potentially be extended to Boussinesq. So now you have an active scalar, but the active part is in some sense mild. So you're forcing
Yeah, that's
because you admit, when I asked Jacob, he said that he was thinking of it, but there hasn't been anything on that. And I can see you have made progress on the Boussinesq part. So I wonder if you see that there is maybe a way to do that.
Yeah, no, it's a very good question. And so you say, because I think like if you can, you don't linearize really around a solution of whatever, you just plug as an external velocity field.
Exactly.
What is going to happen is you should, I don't know, maybe you don't observe one of the linear terms, for sure. You won't observe one of them. And so you will quite likely lose this important feature of wave structure, the wave structure we have. So I don't know for the actual Boussinesq with an external velocity field how the shear flow influence the natural wave structure of Boussinesq. But it is a very good point, and I think it's interesting.
Thank you.
Any more questions? Siming. Hi.
Hi, Siming. I cannot hear you. You're muted.
Okay.
Oh,
sorry.
yeah.
May I ask a question about your final construction there? The F and G in the nonlinear equation. Yeah, just some notation. What is delta NL minus delta L? What is that?
Yeah. I'm sorry. Here I was a bit sketchy. So delta L, it will be the Laplacian on the nonlinear change of coordinates. So recall that now you're not doing the change of coordinate of Couette, but you're doing the nonlinear change of coordinates. So the differential operators now will involve factors like coefficients, which depends on the solution itself. And we somehow this delta NL minus delta L is quantifying what is the error you are making by using the linear operators, which is the delta L without the nonlinear part. And here, so the difference between the nonlinear Laplacian and the linear Laplacian. So the linear Laplacian, sorry, the linear Laplacian is this one, right? And the nonlinear one, imagine that you have, for example, here V prime, which is the first derivative of the velocity. Therefore, delta L minus delta L will have like a 1 minus V prime. So yeah, I didn't write it. I think I cannot even write here.
So you use the classical multiplier to treat the red part, and then something else to do the blue part? Or?
Yeah, no, indeed, like to treat the red part with
classical one? Yeah.
No. Like here, I didn't write because it's kind of awful, but the multiplier we had to construct is based on on the Boussinesq system. And in particular, it has different regularity imbalances. So it is not the classical multiplier of Bedrosian and Masmoudi. We have to reconstruct the toy model based on basically what is the worst case scenario in this nonlinear case. For the sake of time, I just show you what happens in the homogeneous case somehow. And instead here, you need to consider what is the worst case scenario coming from this nonlinear term. So you need to reconstruct the cascading mechanism that will give rise to another Fourier multiplier. You should expect some different regularity imbalances because now some regularity is encoded inside this essentially a fractional Laplacian of the vorticity. So indeed, the weight and the model are different with respect to Bedrosian and Masmoudi.
So it is not defined in this picture, the weight.
It is. Yeah, no. It is this one, but Bedrosian and Masmoudi here, instead of having this plus 1 alpha, for example, they have plus 1.
Oh,
it is really. It is. Yeah. It is like a really technical point, but if you want, I can explain you more details.
Thank you.
Thank you. Any more questions? Let me scan the audience. No, seems not to be the case. So we thank Michele again.
Thanks.
Very nice. So the second speaker is Gennaro Ciampa from BICAM, so the Basque Center for Applied Mathematics in Bilbao. And the topic will be the strong convergence of the vorticity for the 2D Euler equations in the Inviscid limit. So please, Gennaro.
Thanks, Gianluca, for the introduction and especially for the invitation. It is a very nice workshop. So today I'm going to report about the joint work with Gianluca and Stefano on the vorticity of Euler equation. So let me start by introducing the main character of the talk. So here on the left, you can read the Cauchy problem for the vorticity Euler equation. So omega is the vorticity of the fluid we're considering, U is the velocity, and we are going to deal for simplicity with solutions which are defined on the two-dimensional torus in space, and the solutions are global in time, in the sense that capital T is as big as we want but finite. Okay, a peculiar fact of the 2D case is that the vorticity solves a kind of transport equation which is nonlinear and non-local due to the coupling with the velocity, which is the so-called Biot-Savart law. And the problem we want to address is to analyze the famous vanishing viscosity limit in the sense that we consider the corresponding system for the Navier-Stokes equation. So basically on the right hand side you have a diffusion, and nu will be for us the viscosity of the fluid, and we want to understand the behavior as the viscosity goes to 0 of the solution of the Navier-Stokes equation. So before to continue, let me do just a brief recap about the known theory of existence uniqueness. So it's a rather old result that smooth solutions exist and are unique, and but on the other hand, for weak solutions, the only existence uniqueness result is the one of Udovich, and it goes back to 63. So while for the existence part, there are several results under several integrability conditions on omega 0, and the one which will be important in our analysis is the one of the Verne-Maida for vorticity which are unbounded. And let me recall that up to date, there are several partial results of non-uniqueness, and many of them were discussed yesterday in the talk of Maria Colombo, but we still don't know exactly what happens when the vorticity is unbounded. So let me comment just a little bit the result of the Verne-Maida. So essentially, they, besides many other results, they prove the existence of weak solution by relying on these three a priori estimates. So the first one comes from the energy inequality for Navier-Stokes. The second one is due to the fact that the vorticity solves an advection diffusion equation with a divergence-free vector field. And the third one comes from the Calderon-Zygmund theory, since the derivatives of the Biot-Savart kernel are Calderon-Zygmund operator. So you can bound the gradient of the velocity in LP with the LP norm of the vorticity. So basically, what the Verne-Maida has proved is that with standard compactness argument, you have that up to a subsequence, the velocity field converges to a vector field U strongly in L2, while for the vorticity you have a weak convergence toward the A limit function omega. So our goal is to prove in a quantitative way that actually the convergence of the vorticity is strong in the case in which omega is not bounded. And in particular, we will prove the convergence towards a suitable function, let's say. Since the problem is that a priori, we don't know if the limit function omega is a solution of the vorticity Euler equation. In fact, I think all the people in the audience knows that the nonlinearity in the Euler equation in velocity form is U tensor U. So the strong convergence for the velocity is enough. It is enough to pass to the limit in the integral formulation, while this is not always the case for the vorticity. In fact, if you write the vorticity equation in a distributional forms, you can see that the problem is in the nonlinearity. So this with convergence is enough if P is bigger or equal than this number here, 4/3. So the first issue, let's say, in this type of question is to understand what is the limit omega, if it is a solution, and in what sense. Okay, there is a huge literature about strong convergence and rates both for the velocity and for the vorticity. Let me just say a few words on these last two papers. So the first one is a result of Constantin Drivas and Alghindi, which somehow inspired our analysis. So they were able to show strong convergence in the case of a bounded vorticity, so in the Udovich class, and they also, in their work, they also provide a rate of this convergence by assuming some Bezoff type regularity on the initial datum. While the second one, due to Nosser, Spyglass, size, and Wiedemann, was obtained contemporary to our result. So they also proved the strong convergence for unbounded vorticity, so in the out of the Udovich class, relying on an approach which is very close to the Invariance theory for the transport equation. And the drawback of this kind of approach is that you don't quantify the rate of convergence of you don't quantify the convergence of the vorticity, and they also consider the forced Navier-Stokes equation in their case. Okay, so it will be crucial in our analysis the Lagrangian property of the solutions of the Euler equation. So for smooth solution, it is well known that the system of PDEs is equivalent to this system here of ODEs. So you can find the flow of the velocity, construct the vorticity as the superposition between the initial vorticity and the inverse of the flow, and then you reconstruct the velocity via the Biot's law. And we want to give a similar, the same definition for in the weak case. And to do that, we need to introduce the flow of Sobolev vector field. So this is the theory basically of Verneuil-Léon's. So we define for a Sobolev velocity field, we assume it is divergence free for simplicity. Its regular Lagrangian flow as a solution of this ODE, which also satisfy this property here. So this map is measure preserved. So as you may know, this in the smooth case, let's say whenever U is Lipschitz and divergence free, this condition follows from the definition of solution of the ODE. But nowadays we know that this is not always the case. So we need to impose this condition to somehow select the good flows. So we did with this definition in hand, we can define Lagrangian solutions of the 2D Euler equation in the following way. So for a fixed initial vorticity in LP, we say that a couple omega is a Lagrangian solution if we have this Lagrangian representation for U and omega. So basically, we are not asking to omega to be a distributional solution to the equation. We just impose this formula. And because of the Verneuil's theory, since U is a Sobolev vector field, we can always define this kind of solution. And also for a fixed velocity field U, its regular Lagrangian flow is unique. However, so it may seem a trivial property, but it is not actually. So you may ask when a weak solution of Euler is Lagrangian, and basically it is true whenever P is, so it is true for every weak solution whenever P is bigger than 2. This is because you can apply, in this case, you can apply the Verneuil's theory, so every solution is renormalized in particular Lagrangian. However, for less integrable vorticities, this property may depend on the way you construct the solution. And it has been proven that actually limit points of the vanishing viscosity method are Lagrangian solutions. So even though you don't know if the solution in the limit is unique, you know that vanishing viscosity solutions are Lagrangian. And this property actually is not trivial even at the linear level, as has been proved by Modena, Saktik, and Segelidi in a series of papers. In fact, they were able to prove the existence of distributional solutions of the transport equation which are not transported by the flow if the integrability of the vector field is very low. And actually, if you do the computation, you are in Modena Saktik Segelidi setting if P is less than is 4/3. But still, the existence of solutions which are not Lagrangian is not known for Euler. Okay. So some preliminary comments. What we are going to do is to prove that the strong convergence in the case of abundant vorticities, and in particular, we will prove the strong convergence toward this Lagrangian solution. And our approach will rely strongly on the so-called stochastic Lagrangian formulation for the Navier-Stokes equation. So basically, since we have a stochastic Lagrangian representation for the solution of the Navier-Stokes equation, so with that, the problem of the strong convergence of the vorticity translate into find stability estimates for a stochastic flow towards the deterministic one. Okay. And I need to introduce what is the stochastic flow. So for a given fixed probability space with an adaptive Brownian motion, we define the stochastic flow as the solution of this backward stochastic differential equation, where nu is the velocity is the solution of Navier-Stokes. So it is a smooth velocity field which is divergence free, and in this case we are in the setting of strong existence and pathwise uniqueness for x nu, which means that we can find the solution of this SDE on every given probability space with any given adapted Brownian motion. So in particular, the probability space and the Brownian motion are not part of the solution. And moreover, we also have that this stochastic flow, thanks to the divergence-free property of the velocity, is measure preserving. So by the famous Feynman-Kac formula, then we have that this guy here solves the Navier-Stokes equation, and then the Lagrangian formulation of Navier-Stokes is this one. Okay. So, few words about constant derivatives in the result. So, in their proof, in order to provide a rate of convergence, they also rely on stochastic Lagrangian representation, and what they do basically is to find some losing estimates for the regularity of the stochastic flow, which translates into a uniform bound for the vorticity in this Bezoar space. So the exponent so as the decay as the time goes to infinity. And by a simple interpolation inequality, then they obtain this rate. So why did I comment this result? Because as you will see in our result, something which is good, I will say, of our result is that we don't need to require any regularity on the vorticity, but our rate will depend on the modulus of continuity in L1. Will be clear in a moment. Okay, so the first result is the following. You give me a vorticity, initial vorticity in RP. You consider also an initial datum which may depend on the viscosity which converges strongly in RP to this omega 0. And then you consider the unique solution of the Navier-Stokes equation. So we know that at least up to subsequences, they converge to a Lagrangian solution of Euler. So let us fix also one of the possible limit points. And the result is the following. So the difference between the solution of Navier-Stokes and Euler can be controlled in this way. So you have a small parameter delta, which is due to the fact that omega 0 is not smooth. You have the difference between the initial datum. And then what you actually expect, you have that you can quantify this convergence, but it depends on the difference of the velocities. Why do you expect that? Because you don't have uniqueness at the limit. So at least you need to know which solution are converging. So as I already said, the idea is of the proof is to rely on stability estimates for the flow. So you know that the limit is Lagrangian, and basically what you do by simple inequalities, you can estimate the difference between omega nu and omega with the difference of the flows. And now we will find, so we will quantify this convergence for the flows in relying on an approach which reminds the theory developed by Gianluca and Camillo for the ODEs, and which was then extended to the case of Stochastic, in the probabilistic case by Champagnat and Jabin a few years ago. So we write the difference between the stochastic and the deterministic flow. We obtain this as the here. So by defining this logarithmic distance between the flows, we want to find the estimate on this quantity here. So what you do, you estimate it from above by relying on Ito's formula. What you get is this guy, which is the same you find in the deterministic case, let's say, and then this is the contribution due to the Brownian motion. Okay, epsilon, of course, is a parameter that for hour is fixed, and then it will be chosen in a proper way. On the other hand, you can bound this guy from below in this way. So you have that the measure of the set where the flows are far from each other of a quantity square root of epsilon can be bounded by this quantity over log of epsilon. So let's find, the idea now is to find a uniform bound, so a proper bound for this guy from above. So continuing here, we have that we split this guy into terms. For the first one, we use this inequality on the difference quotients, which rely on the maximal function. So basically, what you do, you don't consider epsilon here. You estimate with the maximal function. You use the fact that the flows are measure preserving, and you bound everything with the gradient of the velocity. On the other hand, you can bound this other guy by erasing the difference of the flow, so you get the difference of the velocity over epsilon. So what you get in the end is this inequality here. So now, to find to quantify the convergence of the flow, basically you split the integral where the flows are close, where the flows are far from each other, and you use this estimate, this previous estimate on the super levels, to get in the end that they converge like 1 over log of epsilon nu, where epsilon nu is chosen accordingly to nu in this way. So it is the maximum between the square root of nu and the difference of the velocities in harmonic. Okay. Let's now move to the second result. So the rates. So now we assume that the vorticity is bounded, and we want to use so the more integrability for the vorticity, which translates in more regularity for the velocity fields, to obtain an explicit quantification of the convergence in terms of the viscosity. So what you get is that there exists a function, which is a modulus of continuity, which depends on omega 0 as a function, so not just on its norm, such that the difference between the two solutions is controlled in this way, where delta nu is this one. So in particular, this delta nu is the rate of convergence found by Sheman in his paper. So it's the rate of convergence for the velocity. So we do a similar analysis, but instead of the logarithmic distance, we just consider the Euclidean distance for the difference. You apply Ito's formula, and what you do, you use the fact that the constant appearing in the Calderon-Zilmond inequality depends linearly on P when P is large enough. Then, by defining this quantity, you want to find you find an integral inequality, which derives, of course, from this equality here, which is the following. So this guy here, alpha nu, can be bounded by delta, because remember, alpha nu is defined in this way. So by Sheman, you have a rate for this difference. And then you choose, you are free to choose P as big as you want. And since this y nu, okay, this is a subscript, not a superscript. So you choose P to be 2 minus log of y. And by using the Osgood's lemma, in the end, what you get is this double exponential for the convergence of the flow. So what is left to do is like before, you split. So you compute the difference between the Navier-Stokes solution and the Eulerian one. You split the integral where the flows are close and where they are far from each other. So for this guy, you use the stability of the flow, while for this first one, you use the modulus of continuity of the translations in L1 of omega 0. So since omega 0 is bounded and we are on the torus, it is in L1, so we know that this modulus of continuity exists. And you finally obtain this inequality here. So in the end, by choosing epsilon in a proper way, you obtain the bound. Okay, so let me finish with just 2 remarks on the proof. So as you already said, we didn't need to propagate any regularity, relying on this modulus of continuity, but of course we don't improve the rate of constant derivatives del Guindi. It is very similar because it's a double exponential, but we don't really improve it. So the question of whenever the rate is optimal or not is still open. And the second one is that this Lagrangian argument is completely linear. In fact, the nonlinearity plays a role only, so the nonlinearity is good in this case because give us regularity via the Biot-Savart. And that's it. Thank you for your attention.
Thanks a lot. Are there questions or remarks? I see Lucio, so raised hand. So can you unmute yourself? Hi.
Yes. Hi. Very nice talk. And I wanted to ask, because basically once you pass through the stochastic Lagrangian formalism, this study of the small vanishing viscosity limit somehow becomes a study of a small noise limit. So in the probabilistic literature, in the case of small noise limits, there are many tools. Like there is the friendly Wenzel theory, and in particular, you can try to study either a large deviation principle underlying this small limit or the fluctuations. So my question was whether you consider any of those. And the reason why I'm asking is exactly related to what you saw in the end regarding the optimality of the rate. Like in the stochastic setting, usually one establishes optimality of suitable rates by showing that the fluctuations around those rates are nonlinear. Basically, you say, you know, the large numbers is optimal because of central limit theorem. So maybe here something similar might be applicable in principle.
It is a very nice remark, and actually we didn't look to this to the large the fluctuation. So it's something that we definitely have to study. But now I have no idea if they can provide an optimal rate in our case. But if you say so, I trust you.
No, I mean, I don't know. In this case, there is, I mean, there is, of course, a nonlinear transformation in between somehow. So I mean, it's not clear. But yeah, but it might already strongly hint at.
Sorry?
It might already strongly hint that something should be optimal if you have non-trivial fluctuations. And of course, you're taking an average in the middle, so that could still destroy something in principle, and you could get higher cancellations. But, yeah.
Thank you.
So any more questions or remarks?
Hi, Gennaro, I have a question. Can you control, so you use the B to infinity norm at some point, or at least your approximate solution are in B to infinity, right?
Sorry, can you repeat, because I didn't hear you properly?
Can you, sorry, it's my mic. Can you hear me now? I'm just, you're using so your approximate solution are in B to infinity, right?
No.
In the Basel space, the Navier-Stokes solution.
Those are the solutions of Constantin-Rivas-Delghini.
But you don't, so you cannot say anything about, so your solutions are just in LP?
They are just in L infinity.
Okay.
They are just in L infinity.
Okay.
So in every LP space, since we are on torus. What you can say is that, okay, these modulus of continuity, given the regularity of the initial datum, you can find it. In the case of Bezos space, I guess that will be something like power to nu to the power s will be.
So my question is that if you assume it's also in B to infinity, okay, so you have, well, I mean, which certainly, okay, so on the torus, it's also in B to infinity, right? Because it's in L infinity. Okay. So, but my question is, it's a control on the B to infinity norm as viscosity goes to 0, because that could be relevant for the spectrum, from the energy spectrum of the solution. So I was wondering if, you know, you've thought of also controlling. And the difficulty is that these norms are not of transport type, but there is work of Danchan on transport in Bezos spaces. Mm-hmm. So for the linear case, you can control what happens in the viscosity limit in the Bezos space, but I was wondering in this case what happens.
No, we didn't analyze, so we didn't think about any regularity because our goal was to provide a quantification without requiring it just in L infinity. But of course, I mean, at least by the work of Constantin-Rivas-Delghini, you can say that there is propagation. I mean, there is a losing estimate, so there is not really a propagation. And since the estimate on the Bezos norm is uniformly, somehow you should get this regularity also for the solution of Euler.
So they have a uniform norm in viscosity on the?
Yes.
Okay. Okay.
Yes, it's.
Okay. Yeah, I missed that.
Yes, on this quantity here.
Oh, I see. Okay. Okay. Thank you.
You're welcome.
Thank you. So any further questions or remarks? So thank you again, Gennaro. Okay, I would suggest if you, Paul, are ready, we may start. And the next speaker is Paolo Bonicato from the University of Warwick. He will talk about moving currents on the lead transport equation and the geometric Rademacher type theorem. Please, Paolo.
Thank you. Good afternoon, and thanks, Gianluca, for the introduction. And of course, thanks for the invitation. It's indeed an honor to take part in this conference. And as it has been said quite a few times now, and I do regret very much that we cannot meet in Pisa. And I can just hope that we have a better time ahead of us, and hopefully we'll be able to resume in-person meeting very soon. So today I would like to tell you something about a work, an investigation that I've been conducting for quite some time now over the pandemics. And as you see from, as you can read on the slide, it's joint work with Giacomo Del Nin and our common postdoc supervisor, Philip Rindler, here at Warwick. So the big, say, the overarching goal of this project is, in a nutshell, to identify, to find, and to explore yet another bridge, say, between two different, though very close areas of analysis, of mathematical analysis, namely calculus of variations and, say, material sciences on the one hand, and PDE, and more specifically the transport world, on the other. And so before diving into the matter, a very quick outline of the talk. So I start providing you with some motivations behind our study. and with a very quick, mostly notational recap on the theory of currents, of Euclidean K currents. And then building upon this, I'll be able to write down our equation, the equation that we want to study, which is indeed a PDE of transport type on currents. And then I'll finally tell you something about this geometrical Demarket type theorem. So this is something we have found along our investigation. And if time allows, I'd like to spend a few words concerning presenting you some glimpses from its proof. So without further ado, let me start. And our study really pivots around the understanding of the mechanisms which lie at the very basis of deformations of solids, actually of permanent plastic deformations of solid materials. So if you want, it's a question that stems from material sciences. And in this regard, a crucial notion is the one given by dislocations. So I don't want to enter into the details of these, and I'm by no means an expert in this field, but one way in which one can, a possibility where if one wants to understand dislocation is to think of them as topological line defects in the lattice, in the crystalline structure of a material. Well, to be slightly more precise, say, and to give hopefully a better idea, one way to understand is dislocations is if you give yourself a loop, say a circuit, and you compare essentially, you start from a circuit in your material, and you count the number of atoms or the atomic bonds that such circuit crosses, and you compare somehow this number with some reference configuration, for instance, the perfect lattice. And every time that you encounter a mismatch, every time that you see that some errors occurred in this computation, then actually you have more or less by definition a dislocation. And of course, people have been trying to understand and formalize dislocations at a mathematical level for quite some time now, and with an increasing level of sophistication. And nowadays, it's one of the possibilities, which is rather common, is to model dislocations using geometric measure theory, and more specifically using one-integral currents. So you will see in a moment that one-integral currents represents, are sort of, roughly speaking, they are geometric one-dimensional objects. And since dislocations move according to the forces that are exerted on your material, on your specimen, essentially we are looking for models, for evolutionary models on dislocations. And among the many evolutionary models we have selected, we wanted to study the transport. And so since I've just said that dislocations are modeled by currents, it's natural now to try to seek a theory for transport of currents. And let me emphasize, this is somehow I want to make to underline this, that indeed dislocations are indeed one-dimensional, as I said, and of course they are one-dimensional. And if we see this from the physics world, they are one-dimensional singularities in a 3D material, in a 3D setting. So the problem, the mathematical problem, will truly be codimension too. All right. So let me, as promised, let me give you, let me brush up a bit the theory of currents. And this is, say, just to lay down the notation that I'll be using during the talk. So currents, as most of you know very well, are linear continuous functionals on the space of compactly supported smooth forms, differential forms. So it's, if you want, it's an analog, some vector valued, multi-vector valued analog distributions. And indeed, this is the standard definition, and I'll be using this notation, which is kind of standard, I guess, of D subscript K to denote the space of currents. Currents are also known to be, are also called, say, generalized surfaces. And there's some analogy, I mean, pretty much in the very same way in which one can understand distributions as generalized functions, if you want. And this analogy with surfaces allows me to introduce two objects to, well, quantities that play a big role in the theory of currents. So on the one hand, we have the boundary operator, which comes sort of naturally defined. It's defined as the adjoint of the RAM exterior differential, and you can check that such a definition. If you start from a K current, it gives you a K minus 1 current. And it represents, I mean, with this analogy of surfaces, the boundary will really stand for the boundary of the surface. Instead, a quantity that generalizes somehow the notion of area of a surface is what is called the mass of a current. And as far as this talk is concerned, we will always be working with current with finite mass. And within this regime, so whenever we assume the finiteness of the mass, the analogy with that I was saying, so the analogy with vector value distributions is actually effective, can really be proved. And if you want, and also some, let me mention these also as examples. Zero currents with finite mass are really nothing but measures, scalar measures, while instead K currents with finite mass can be written as measures with values in K vectors. All right, so it's nothing more than that. Actually, to be even more precise, for this within this talk, I'll restrict my attention to special subclasses of currents. Well, we could consider normal currents, which are defined as the currents for which both the mass, the current itself and its boundary are finite. But actually, the talk will really be concerned with integer rectifiable currents. And integer rectifiable currents can be, if you want to define this way, so the representation as vector valued measures that I was mentioning on the slide before, as this special form. So it's a vector valued measure of this form with the Hausdorff k-dimensional measure restricted to some k rectifiable set. The multivector is given by an orthonormal basis of the approximate tangent space to the rectifiable set. And if you want, we can multiply everything times an integer valued density. So let me maybe simplify a bit the thing and give you, I mean, here's a informal picture that I would like you to keep in mind for the duration of this talk, since I'm basically presenting you this case. So whenever I'll be saying something about an integer rectifiable 1 current with 0 boundary in RD, there's really no loss of generality if you think to it as just a collection of loops, right? So it's a collection of Lipschitz loops that are actually even injective, apart from the start and ending point. And this is a theorem that you can prove, but this is the picture that I would like you to keep in mind when I'm saying integer rectifiable boundaryless 1 current, right? And I need at this point one more definition on currents. I'd like to introduce an operator, yet another operator on space of currents, which is this Lie derivative operator. And it comes, I guess, as no surprise that it's defined once again in duality. I mean, it's the Lie derivative. So I have to specify, I have to fix a vector field B, which is assumed to be given. The Lie derivative of a current with respect to B is simply defined to be the adjoint up to minus sign as the Lie derivative on, as moving the Lie derivative onto the test form, right? And the Lie derivative of a form, of a smooth form, is classically defined. And it's just, I mean, one possibility, it's the formula that I've written here on the slide. And it's ultimately the Lie derivative of a form is a sort of, it's measuring how the form changes along the flow of the vector field, right? This is standard notation, standard notion of differential geometry. And let me say that for those of you who are more acquainted, say, with currents and who know about the wedge product of currents, there's actually an explicit formula that one can, let's say, a fairly explicit formula that one can get for the Lie derivative operator, explicit in terms of the vector field and the current and its boundary, if you want. And it's precisely the one that I've written in the blue box in the slide. And it can be proved just dualizing the Cartan's magic formula, which is also written on the slide, and it relates, if you want, the Lie derivative of a form with the differential and with the contraction with the vector field, right? So just dualizing the Cartan's formula, one can obtain this explicit formula for the operator. Well, I have introduced basically all the objects that I would like to play with, and it's time now to write down the equation that we want to study. So we want to study the following transport equation, the following Lie transport equation in the space of currents. And the situation is as follows. I suppose that I have current, an initial current T bar, and I'm looking now for solutions that are family of currents T indexed by time, so TT, which solves the transport type PDE that I've written down on the slide. So the time derivative plus the Lie derivative with respect to B is equal to is identically equal to 0. And well, let me say that we've not been able to find, say, a thorough inspection of thorough investigation of this equation in the literature that we have looked at. And so there's something appearing in some slides by François Bochou, and where he deals with the formulation more with K forms and not in terms of K currents. And I like to publicly acknowledge Gianluca for bringing them up and pointing my attention towards them. There's also some, this equation appears also in Kamp-Schulte's PhD thesis of the 2017, where he's studying basically gradient flows on the space of currents, and this equation appears mostly in with C1 vector fields. And it's also very close, this equation, to some work by Jan Brenier, who's not really working on with this equation, but with somehow its representation, its writing coordinates, and it's related to some models involving magnetohydrodynamics that Brenier was studying around 10 years ago. Before going on, let me let me check with you what happens in two particular cases, which I guess are kind of interesting. And let's see what happens in the extreme cases. So let's, so in the two extreme cases, so namely when K is equal to 0, I'm considering 0 currents. And I said that 0 currents with finite mass are measures. So TT is actually something that we can write as mu T, where mu is a scalar measure. And it's a very easy computation to perform, that the Lie derivative in this case is nothing but the divergence of the product B mu. And so all in all, this equation, this PDE that I'm considering in the case K equal to 0 reduces to the good old known continuity equation for the measure mu T. Instead, in the top dimensional case, so D currents, top dimensional currents are actually can be represented by scalar functions, so it's sort of scalar volume, and it can be checked that in this case the operator reduces to the differential derivative, to the directional derivative in the direction of the vector field. And in other words, the PDE in the top dimensional case reduces to the transport equation, to the standard transport equation. So what is this saying? This is saying that essentially we have sort of identified a spectrum between the continuity equation and the transport equation, and something that can be done very easily and that applies to the full spectrum. Oh, maybe there's a question. I cannot hear.
Can you hear me?
Yes, I can. Yes.
Hi. So the question is this: if we are in the smooth case and we have the flux defined by the vector field B,
yes,
is this amounting to say that the solution should be the current transported by the flux?
Can you just wait one slide more?
No, I was trying to understand the meaning of the equation. Okay.
Yeah, no, because it's exactly it's exactly as you were pointing out. That's exactly the content of this slide.
Sorry.
Because if we are indeed in the classical setting, so if we have, say, B is Lipschitz, but if we want, let's say, even C1 for what I mean, it doesn't really mean doesn't really have a meaning here. So in this sense, yes, we can prove well-Poseness results for this equation. It's fairly easy. Namely, we can show that there exists a solution. The solution is unique. This is not completely trivial, but it's still rather easy. And we can actually also write down the formula, which is exactly as Giovanni Alberti was pointing out. It's the push forward along the flow of the initial datum. So I'm transporting the current along the flow of the vector field. Whenever such a flow has enough regularity, for instance, is Lipschitz or C1, in such a way that the push forward operator is well defined. And I have defined here on the slide what the push forward of a current is, and again can be defined in duality with respect to the pullback of a differential form. And it's again worthwhile as a consistency check, it's a sanity check that one should perform, that in the extreme cases such a formula is really encoding the standard formulas for the solutions to the continuity and the transport equation. So I'm not really finding new or inventing new things. It's just the standard. I mean, in the case k equal to 0, the push forward of a zero current reduces to the push forward of a measure. And so it's the solution to the continuity equation. In the top dimensional case, instead, the push forward is actually can be written as the precomposition with the function. And so we have the method of characteristics, say the Lagrangian solution to the transport equation. So there's, however, a problem, I would say, that it seems rather difficult to us to develop a theory for such equation for rough vector fields, somehow parallel to the one that we have for the transport equation, say for the top dimensional case. And this is due essentially to two factors. On the one hand, there's a complete lack of a priori estimates. And on the other hand, if you want, we have not enough regularity, for instance, of the regular Lagrangian flow, which we have seen it's very far from being Lipschitz. And so it's not easy to understand how such a formula, such a formula could be extended to less regular situations. Nonetheless, I should say, I'd like to point out that there's a number of there are a couple of interesting questions that one can still pose on this equation and would like to investigate, and that's precisely what we are going to do right now. And I'd like to tell you about this Rademacher type theorem that we have found. And the Rademacher theorem stems from the following elementary observations that one can make. And that's indeed rather easy. So suppose now that I am given a vector field, a bounded vector field, and a family of integer rectifiable k current, which solve the PDE and say, for simplicity for a moment, let us assume that they are also boundaryless, right? So the boundary is zero, and they solve the PDE. Then it's easy to check that the map from the reals to the space of integer rectifiable currents is Lipschitz. And of course, I'm saying Lipschitz, so I should define at least a distance, right, on this the set of currents. Otherwise, it's not meaningful. One cannot understand what I mean by saying Lipschitz. And the distance that I will consider is a very standard distance on the set of currents, which is the flat distance. Actually, since I'm restricting to the boundaryless case, I'm considering the homogeneous flat distance. And its definition is written down on the slide again, and it's if you want, it's very close. It's a generalization of the Wasserstein distance between two measures. And it's also, let me say, it's a rather natural object to consider when working with currents, because it can be proven that the flat distance metrizes the weak convergence of currents on bounded sets. So, I mean, it's sort of fairly natural quantity to consider in this geometric measure, this geometric setting, say. And an idea, I mean, if you want an intuitive picture that you might want to keep in mind again, is if you consider two loops, the flat distance between them is essentially the area they loop, I mean, the difference of the areas, right? So in the picture, if you have the blue and the red loops, the area shaded in blue is the flat distance between the two. This, I mean, roughly saying. So this is an intuitive picture again that you might want to keep in mind. The question that we are asking now, so because you see, we have seen that if we're given a solution to the PDE with, say, a bounded vector field, then the map is Lipschitz. What we're asking is, does the converse hold? That is, so suppose now, let me change a bit the point of view. Suppose that we are given a map, a current valued map, and to every time it's such a map gives me a current with boundary 0, and I assume that such a map enjoys Lipschitz regularity, again Lipschitz with respect to the flat distance. Can I construct a vector field B which is advecting this currents TT, which is solving the PDE for this TT? So if such an object, if such a vector field existed, we could, I mean, it could be thought of as a geometric derivative, right, of the Lipschitz map, and therefore the name Rademacher type theorem. Of course, it's not a derivative, it's not a differential with respect to the linear structure of the space of currents. It carries a more geometric meaning. Say it's simply telling me that these currents are evolving according to it. So again, if you consider the picture that I presented before, so if you have, imagine a collection of loops that are wandering around in the plane or in R3, for instance, you know, your assumption is just this control on the flat distance between them. I mean, Lipschitz regularity of the flat with respect to the flat distance. Can you find an advecting field, a velocity field, which is driving their evolution? And well, the answer, once again, let us start from the basic cases. So in the case k equal to 0, the answer is yes, is affirmative. And it's, I would say by now, textbook classic, because it's one of the ways in which one can introduce the continuity equation, and such a theorem can actually be found, for instance, on the Ambrosio Gigli Savare's book. And our contribution is an extension to this answer to say two other cases. So the top dimensional case is not really that interesting, it's kind of empty, but we are able to cover the codimension 1 and codimension 2 case, right? So the same, the converse holds true. So we do have this Rademacher type theorem for integer rectifiable d-1 and d-2 current. And let me emphasize that indeed in the physical situation, so when the dimension is equal to 3, now every case is really covered. So I would like to spend the remaining times of this talk giving you an idea, presenting you in somehow the heuristic ideas that are behind the proof. And the proof is can be split essentially into two parts. In the first part, I am changing a bit the point of view. So bear with me for a moment, please. We are adopting the level set method. So we are trying to find a substitute for the level set method, which is quite a common tool for studying evolutions of surfaces, for instance, in the mean curvature flow. And we have found a way, we found, say, a substitute which is really tailored to the case of currents. And the situation in the picture is now the following one. So suppose that you start now from a pipe, a cylinder, in one dimension more. So suppose that you're given this k+1 integer rectifiable current in the space-time, right? So here the basic idea is to add one dimension to see what happens in one dimension more. So if you start from such a pipe, from such a cylinder, by using standard techniques in the theory of currents, namely the slicing theorem, you can slice this tube, you can use the slicing theorem with respect to the projection onto the time axis, and you obtain these currents ST, which modulo an irrelevant projection can be identified with K currents, integer rectifiable currents in RD. And now what happens is that taking advantage of the space-time structure, so taking advantage of the fact that you're really starting from a pipe in the space-time, it turns out that you can find a velocity field, you can define a B, which is advecting these slices. And of course, such a field is defined in terms of the vectors that span the tangent, the approximate tangent space to this pipe, to this cylinder, right? So essentially this recipe that I've just presented solves essentially the problem whenever we have a space-time structure, right? So the proposition, say the lemma that we have obtained is that whenever we start from a rectifiable, an integer rectifiable k+1 current, we can find a vector field B, which is advecting its slices. And I guess you see now that the problem, it's now been somehow shifted, and it becomes a rectifiability question in the end, because so I want to start from my collection of loops that are wandering around, and I want to find a way to pile them up in such a way that the resulting pipe, the resulting cylinder, is actually rectifiable, or more precisely, it's a 1 + k integer rectifiable current in the space-time, right? And so this is really a rectifiability issue. And once again, the case where k is equal to 0 is well known. It can be found with, I mean, quite surprisingly, I would say, at least at the beginning, that was our feeling, in this very influential paper by Ambrosio and Kirchheim of the 2000 about the metric currents. And let me say that there is also something, something done by Gerard in these regards. But actually, the same conclusion, so we can pile these loops, we can find these currents in such a way that the pipe is rectifiable, also in the codimension 1 and codimension 2 cases, and this is indeed what we managed to show. And let me just say that in this case, the answer is related to somehow more abstract question that ultimately concerns the very definition of the flat norm. What we really need here is the equivalence between the normal homogeneous flat norm and the integral homogeneous flat norm, and we are able to show such a thing in these cases, relying on well-known, well-established work in geometric measure theory going back to the 80s. This Arden Pitts and this Zworsky paper. And so, all in all, performing this space-time construction and then relying on it to define the vector field, we are able to show this Rademacher type theorem. And I think I'll stop here. I thank you all very much for your kind attention.
Thanks a lot, Paolo. Are there questions? So maybe I start here. Two small curiosities. Okay. So concerning the regularity of the vector field that you get, so you were describing everything for bounded vector fields. So if you have some, so can you define any additional regularity in time of the family of currents and then find additional regularity of, or it's just hopeless?
And I honestly don't know. We have not looked into that. It's something that we should address, because it's somehow it's really sort of ongoing still. because I mean, at the moment we have only looked at this. I wouldn't be able to answer on the spot because you say if you want to improve the direct implication, you have better vector field, you want a better behavior on the space of currents, or
no,
vice versa.
I was wondering
you want
about the other. So if you impose some condition, but then not only time regularity, maybe some additional structural regularity on the currents, which I don't know how much sense they make. So whether you get a vector field which is, say, space regular in some way.
This I don't know, because it wouldn't be. I mean, I cannot imagine more restrictive, say, conditions. I mean, I find already quite restrictive the fact that we're considering integer rectifiable currents to some extent. So, I mean, I don't know what, I mean, I have no clear idea of which class which regularity I would assume.
Like a regularity, geometric regularity on the support, or does make no sense as a submanifold? I don't know, I'm very speculating.
Might be, yeah. I mean, yeah, it's a question one can address, actually. Yes, that's I wouldn't be able to give you an answer on the spot. Yeah.
And the other thing I was wondering, but still a bit in the same vein. So if you are looking at the case of codimension 1, then you restrict so inner 2 at closed curves, or say in inner 3 to say to surfaces codimension 1, which are countering some area, some volume. So then you have a correspondence in the smooth case between divergence free for the velocity and conservation of the volume or of the area. Do you see anything like that in your construction, so that if you have an evolution of the currents which is conserving the area of the enclosed portion of the plane, then you get a divergence-free vector field, or you can get a divergence-free vector field?
I think that this is, I mean, the divergence is not anymore the right quantity to look at, right? I mean, the divergence is related to the determinant of the Jacobian, and the determinant is what appears is the minor of biggest order. So it's what appears when you consider essentially top dimensional case. You would have to look at the minors of the gradient of the Jacobian. I mean, it's slightly more involved. There is no more a clear connection between preserving volumes, I guess, because the determinant is not. I don't know if it makes sense to you what I was referring to.
Yeah, because I was still thinking of a transport, and now I was trying to see that for n-1 currents, but that's for d-1 currents, but that's not the right thing to do.
Yeah, because and this is that's really the point where where you don't have a priori estimates, essentially, because the divergence is really controlling the full determinant of the Jacobian, so you get a priori estimates, but otherwise.
Yeah. Thank you. Giovanni has another question. So Giovanni, you raise your hand, or?
Yes. Okay. So I had one question and well, two questions. One concerning also the model, but concerning mathematics. Given what you already said to your answer to Gianluca, what would be the right quantity to keep under control? When
that's
you say preserve to make sure that let's say that the length of the curve explodes at most exponentially. So if of course not, but then what?
I am afraid, and I mean, I think it's the tangential divergence.
In every direction, right?
Right, that's the problem. So a priori, yes, in every direction, because you don't know.
Does that amount to say that the vector field must be slightly less than Lipschitz?
I do suspect the same, but I'm not able to prove it rigorously. But yeah, it will be. This is the reason why you really. I mean, you lost the a priori estimates, because in some sense you would have to control the divergence in the directions you're looking for, and so that's not clear. But I think that that will be ideally the right quantity to look at and to keep under control. But no serious idea on how to do it.
And the other question was, okay, let's say somehow it seems to me that considering rectifiable currents is like in the case of transport equation is considering direct masses somehow
precisely
worst possible case. Why don't you look, I mean, at least on a purely theoretical setting, why don't you look at something diffuse instead of something concentrated?
We started considering the case of Dirac masses because we want, I mean, we were, say, more acquainted with with integer rectifiable currents, and we wanted to consider them because somehow I mean, our idea was that it was a better case, a better model to look at in first place rather than normal diffuse thing. But I guess, I mean, I do believe that in the zero case, in the case k equal to 0, the result should be fairly general, even in, I mean, in Ambrosio Gigli Savaret. I don't think you really need to assume that they are Dirac masses. For the rectifiability, if you follow our approach in the case k equal to 0, then instead you have to look at the to restrict the rectifiable case.
Okay. And then one final question concerning the model.
Yes.
If you really think to apply that to these locations, okay,
yes.
Whatever scale you put them, because on certain scales, presumably they are quite diffuse. But what could be the driving force? I mean, the vector field be technically, what should be? Something related to the stress, or?
I think something. I mean, something that goes like the tensor product of the Burgers vector with the orienting to the normal, to the current. I don't really know how to write down the field.
The question is why should the dislocation move? What makes them move?
Yeah, I mean, what makes them move is the force that you exerted on the material, right? And then I think that you have.
That matters. But then, what is the driving force inside?
This I don't know. Honestly, I don't know. I don't know. Actually, that's a fair. That's an absolutely fair question, because it's also one thing that one should wonder is it really transport of this location, or should we look also at other evolutionary models for this location? This is something that we are also. I mean, I do believe that it's not completely correct to consider transport of these locations. That maybe there are, because in the end, maybe what is really look at is a more gradient flow. There's some energy acting. There's some energy that is giving you it's moving, that allows you to study the movement. But so this is an absolutely fair question.
Can I make a comment here? So you're talking about elastic dislocations, right?
I'm talking about, sorry?
Elastic dislocations. In the elastic sense, you're talking about crystals, right?
Yeah, more on the plastic, I would say. It's
well, okay,
permanent,
yes, but still. So the Burgers vector is a displacement, typically. It's not a velocity. It's the slip relative of, so if by how much you have moved relative to the
mistake, right? That it's the mistake.
Yeah, exactly. So yeah, so yes. in elasticity would be the displacement. So it's really not a velocity. So that's not.
But I think that there is a way to reconstruct a velocity starting from the Burgers vector, right?
That's possible. Yes.
I don't have the formula.
Yeah, that's possible. But I'm just saying that you can't just take the Burgers vector.
No. I didn't mean I didn't want to say this. No. But I think that you can construct a model where you define the velocity in terms of the Burgers.
And I think that the gradient flow is more physical.
Perhaps yes.
Good. Any further questions for Paolo? Okay, so if not, we thank Paolo again. Welcome back, everybody. The next speaker will be Theodore Drivas from Stony Brook University, and he's going to talk about remarks on the long-time behavior of 2D Euler.
Okay, thank you very much for the for the introduction and the invitation to speak here. It's an honor. Right, so I'll talk about some results sort of centered around understanding some aspects of long-time behavior in 2D Euler. And this is going to be a collection of joint works, some of them with Peter Constantine and Dan Ginsberg, others with Michele Dolce and Tarek El-Gindi. So let's start just with the equations. So I'll be considering bounded domains, possibly with some smooth boundary. The 2D Euler, well, the Euler equations are this system here. It's divergence free, so incompressible, and the velocity is tangent to the boundary, so it's non-penetrating. And in 2 dimensions, as everybody here knows, there's this simplification that at each moment in time, you have a Hamiltonian for the divergence-free vector field U, which is called the stream function. The velocity is just the skew gradient of it. And that means that level sets of the stream function, which are called streamlines, coincide with the integral curves of the vector field U. So U is just pointwise tangent to these streamlines here. In 2D, there's the simplification that the vorticity is, I mean, as regarded as the 3D vorticity, is just pointing up with a scalar prefactor. So it's just up or down. And that scalar prefactor omega satisfies a transport equation. So it's just moving around, pushed around by the velocity field U. And this equation can be closed as a non-local equation for the fluid's motion by using the Beer-Savart law to say that the velocity is recovered by this integral operator on the vorticity. And of course, if things are smooth enough, it means that the vorticity has this Lagrangian representation that we heard a lot about earlier, namely that the vorticity at a later time is just something on the orbit in the group of volume-preserving diffeomorphisms of the initial data. Okay, and we'll talk more about this viewpoint throughout. Okay. So the starting point for studying these equations is to think about the invariance of the motion. And I would say that there are 2 known robust invariants. So the energy is one of them, and Casimirs are the other. So energy is just the L2 norm of the velocity field, and Casimirs are any continuous function of the vorticity when integrated over the whole domain. And by robust, I just mean that these things hold for any bounded domain omega where you have tangency of velocity. So it doesn't require that the domain have any extra symmetry. One consequence of this Casimir one is that all LP norms of the vorticity are preserved in time, including the sup norm. Now, occasionally, if your domain has some additional symmetries, say the 2 torus or the periodic channel or the disk, then you have some other conservation laws like linear momentum in the first 2 cases and angular momentum in the second. So these cases are important if you're studying long-time behavior on those special domains, but as a general theory, you don't really have any information like this. So these facts essentially allow you to say that the 2D Euler equation predicts globally the motion of the fluid. In particular, you have this classical theorem that says if your velocity is, say, C1 alpha regular, then there's a unique C1 alpha solution for all time. But the norm in this space can grow at most double exponentially. And what this says is that at infinite time, conceivably, you can leave the C1 alpha phase space. So it's not necessarily the right lens to think about persistent structures as time goes to infinity. Although it does tell you some information about what's happening, and we'll discuss that. Actually, Udovich in the 60s proposed, he proved that if you start with bounded initial vorticity, then this propagates for all time. You have a unique weak solution with bounded initial vorticity. And this phase space for the fluid is a reasonable one to study long-time behavior because it's compact. So a unit ball in L infinity is preserved by the Euler equation for all time, and weak limits live inside the unit ball. So this is sort of the point of view that we'll take when we discuss aspects of infinite time behavior. Okay. So a natural starting point when thinking about long time behavior is to understand structures that exist forever, and the simplest such are stationary states. So the stationary states in vorticity form just satisfy the equation transport of vorticity is 0. And if you use the fact that the velocity is, the skew gradient of some stream function, then the condition for being a stationary state is that the gradients of vorticity and gradients of stream are collinear. Okay. And so there are some simple families of these that everybody knows. Shear flows, for example, on the periodic channel are one such, where the velocity is in the direction down the channel, but it can vary in intensity as you go across it. Another such are circular flows on the disk. And all of these have the property, of course, that the gradient of vorticity is collinear with gradient of stream. More generally, you could think of a functional relationship where you specify the functional relationship f between vorticity and stream function. This will obviously have this property. So any such will generate a stationary state, provided you can find a solution of this problem, right? Because since the velocity is skew gradient, the vorticity, which is the curl, is the Laplacian. So it boils down to solving this nonlinear, potentially elliptic problem for a stream function. If you have one, then it's a steady state. It should be said that these are not all of the steady states. It's not necessary that there's a global relationship between vorticity and stream, but this is a very large class, and there are some privileged ones that lie in it, which I'll mention in a second. Just a remark, this is not necessarily a good equation in the sense that it can have one, many, or no solutions. A good example to keep in mind is when f is linear, then this is just the eigenvalue problem. So all of those cases can be seen. Now, the first question that comes to mind is, when you're on a domain with symmetry, often when you see something that's steady or quasi-steady, it seems to adhere to the shape of the domain, it seems to symmetrize. So a natural question is, when do steady states conform to the symmetries of the domain? Now, I'll address this question first for stable, in a certain sense, steady solutions. So they'll take, again, this form, that there's a global f relating vorticity to stream, but this f will satisfy one of two conditions. Its derivative is either between the negative first eigenvalue of Laplacian on that domain and negative, or it's positive. And these families of steady states were identified by Arnold from a geometric consideration. They actually correspond to minimizers or maximizers of the kinetic energy on isovortical sheets. Rather, you could think of on a set of velocity fields whose vorticity is related by a diffeomorphism to the given steady states. So this is the orbit in the group of volume preserving diffeomorphism. The picture is something like this, where you have these sheets cutting energy surfaces, and these guys are maxima or minima. And this imparts some nonlinear stability to these steady states. So you can show Lyapunov stability into the 2D Euler evolution. Okay. So the first result about these is just very simple consequence of these facts, which is that if you're on, say, any Riemannian manifold with some metric and smooth boundary that has a killing field, the symmetry of the metric, which is tangent to the boundary. So think of the disk as one where the killing field is just rotation, where the channel is killing field's translation, or you could have a spherical cap where you have a zonal killing field. In any of these cases, then the Arnold stable solution has to adhere to that symmetry. And the proof is extremely simple. You just essentially take the derivative of this equation and use the fact that killing vector fields Lie derivative along those commutes with the Laplacian, and you show that that has trivial solution. So it implies that if you're on a periodic channel, then the stable guys are shears, disk, the radial, spherical cap, the zonal, and so on. It also says that if you have no boundary, like the torus or the sphere, then there are no Arnold stable solutions. You need some sort of symmetry breaking to have stable solutions there. And I'll just mention that there's other results on symmetries, particularly work of Nadarashvili and Hamel, and then Gomez, Serrano, Park et al. So I won't cover those. Just to keep in mind that long-time behavior, stable things often adhere to symmetry. Okay, so then a natural question is what happens if you don't have symmetry? Let's say you perturb the domain away from symmetry. How do the steady states that are stable perturb? Prior to addressing that question, let me say that there's a very nice paper by Chauffroux and Schwerak where they study this question of flexibility of stable solutions without changing the domain. And they prove that if you take a given stable steady state with vorticity function, say omega 0, and you perturb that distribution function, they show that there's a unique steady state on the orbit in the group of volume preserving diffeomorphisms of the vorticity. So they sort of completely characterize families of steady states nearby a given one using this, but they fix the domain. In some recent work with Peter and Dan, we study this problem not for the orbit of the vorticity distribution, but actually for the orbit of the stream function in the group of these diffeomorphisms. We're also not restricted to volume preserving. So our theorem is that if you have a domain where you have a stable, say an Arnold stable steady state there, then we can wiggle this domain a little bit, and the wiggling doesn't have to preserve volume inside, just the areas have to be the same. And we find a new stable solution here. And moreover, this stable solution inside has the property that the stream function of that guy is given by the stream function of the initial one along at some volume preserving diffeomorphism. So you actually get a characterization, even uniqueness, if you just perturb the stream function a little bit of stationary state on this leaf of deformed stream function by diffeos. And this actually will come up, this will appear later in the talk. So I'll mention this result later. So, okay, it says that Arnold stable solutions are structurally stable. So you make some perturbation of domain or metric or whatever, you find a nearby stable solution that just changes a little bit to conform. Okay. So now that the next question that you would like to think about is time dependence. So what happens if you start nearby one of these stable stationary states? And there's this very nice result in the 90s by Nadarashvili about wandering of nearby solutions in the L-infinity topology of vorticity. So in that the Udovich phase space for Euler. So what he says is that there's a point in L-infinity Xi, such that if you start at a neighborhood of that point in L-infinity, there's a later time where all orbits that start in the neighborhood leave it forever. Okay, so you start close, but then for all later times you leave it. And this point happens to be very close to Couette flow or some other stable, Lyapunov stable shear flow in the domain. So it shows that the dynamics nearby these things, depending on what topology you look at them in, they can look quite different at later times. So the proof of this, I mean, and the construction of this point C is very simple. I'll just quickly explain it. Suppose you have a periodic channel with Couette flow, and you connect the top and bottom of the channel with a line, and you have a little compactly supported perturbation of vorticity along this line. That will be Nadarashvili's Xi. And then the point is that what happens is, because of stability of the Couette flow, this line will just start wrapping around the torus. so spiraling, because the velocity up here is larger than the velocity here, and that's true non-linearly for all time because of stability. So the velocity will stay, bigger than say 3/4 here and less than 1/4 here, and you'll have this relative velocity top and bottom, so you get this spiraling effect of the line. And what that means is that for all times, say after, I don't know, 1 or 2 pi or something, there'll be some of this vorticity supported on this side of the torus. And that can never go away. So it just continues to spiral. It's irreversible. And so what that means is that if you start very close to this particular state, then you'll be far from that particular state in this sense. You'll wander away from it because you have this irreversible winding, and you always have support of the perturbation here. So you can promote this example of Nadarashvili to show also that the C1 alpha phase space, you can leave it at infinite time, which is kind of obvious because, of course, if you have this line that's spinning around, you have stretching of this tube of compactly supported vorticity. These things are getting very close, and that gives very large gradients. So in fact, what you can show is that the C1 alpha norm grows like it would for passive shear, T to the alpha. And okay, it's far from the double exponential growth, but indeed, if you look at Euler through this lens, you sort of lose information at infinite time. Okay, and this circle of ideas studying infinite time blow-up has been the subject of many works recently, and this double exponential rate is saturated due to work of Kiselev and Shvarak. Okay, so that was a statement near a very particular steady state, or a family of them, but still very particular. You could ask more generally, do you have this strong growth in the C1 alpha topology? And this was addressed by Koch and then Margulis, Schnellman, and Udovich. And they prove essentially that almost all steady states are badly unstable in C1 alpha. So they say that any stationary solution is smooth enough, with one caveat that the flow map that it generates is not time periodic, which I'll call isochronal, and I'll explain more in a second. Any such is non-linearly stable in C1 alpha in the sense that I can give an M, big number M, and a small number epsilon, and then I can find a time, depending on those things, in a solution that starts off epsilon close in C1 alpha to the steady state, and it gets M far from C1 alpha in the from the steady state. So in particular, C1 alpha norm grows very large as I like. This doesn't give infinite time growth. It's a finite time statement. We'll talk about the infinite time analog in a second. But it does say that you do experience some very strong filamentation if you're by any steady state at all, except for these time periodic ones. And the idea of the proof is very simple. It's just that if you have some region of shearing in this study, as you go from one streamline to the next, unless the flow map is time periodic, the period along these streamlines will be slightly different, and you can think of this as a local shearing. And essentially, the perturbation is built to exploit this local shearing. I won't talk too much about it. These time periodic ones are somewhat funny. So they were termed isochronal by Udovich, who discussed them a little bit in his works. And they're sort of like fluid clocks. So you put passive arrows of a clock, and at later times they may wiggle, but at time one, say they come back to themselves exactly. And there's a very simple family of these types of solutions. They're obviously very special. You could ask if they, how robust are they? There's a very simple family of elliptical vortices. So the simplest one is just solid body rotation on the disk, like a record player. That's an isochronal flow in the steady solution of Euler, but you can generalize those somewhat surprisingly to this family of elliptical vortices that have the same property. So these things exist, and they may be somewhat rare. I'll comment on that in a second, but they exist. And you could ask I mean, are they also likewise unstable? So it's the only sort of open case from this theorem of Koch. So let's do a small detour on these isochronal flows. In Udovich's work, he made a conjecture about the rarity, sort of about the rarity of them. He conjectured that the only constant vorticity isochronal flows are those elliptical ones I just showed you. They happen to have constant vorticity. And so in a way, it's saying like the profile of the vorticity determines the domain. This conjecture, I'm not completely sure about. There seems to be some evidence, not yet a proof, that this may be false, that there may be other domains with constant vorticity isochronal flows that are not elliptical. But I won't say anything definitive about that. Instead, with Tarek, we made the following conjecture that for any simply connected domain, there's a unique up to scaling isochronal flow. And the motivation for this conjecture is that it's true nearby disks. And so I'll just give the argument for that here. So the first statement is that if you have a disk domain itself, then by one of these symmetry arguments, rigidity arguments, you can show that there's one and only one isochronal flow. So I won't say exactly how that works, but that's pretty simple. Now we can deform that isochronal flow to occupy domains that are small, smooth perturbations of a disk. And that uses the theorem with Peter and Dan. And the basic idea is that first, note that the period of revolution around a streamline, let's call that mu of c. So the streamline is psi equals c. Mu of c is the time it takes for a particle starting on that streamline to return to its position. They're all periodic if there's isochronal flow. And that has an explicit formula in terms of the integral along the streamline of essentially 1 over the modulus of the velocity. And by the co-area formula, this is actually just the rate of change of the area enclosed by that streamline as you vary the level. So immediately from this, you see that if you have an isochronal flow, which means that this period is independent of the streamline you're on, then you see that that implies that the rate of change of this area is constant. So you have that the area grows like the level C. And the point is, if I have a given isochronal flow whose area, say, grows like the level, and I find a deformation of it to a new domain that's on the orbit in the group of volume-preserving diffeomorphisms, then I preserve all the levels and I preserve the areas enclosed by them because the diffeomorphism is volume-preserving. So by applying the theorem with Peter and Peter and Dan in the case of volume-preserving, special case of volume-preserving, we see that these elliptical domains for which the isochronal guys are stable can be deformed to new stable isochronal guys in sort of any wiggle domain you like because it's volume preserving. And this moreover shows that actually all of those, that whole family of isochronal steady states are unstable in the sense of Koch. And so in this sense, because they satisfy in fact the Arnold stability condition. So the vorticity profile function of these deformed guys is essentially in one of those good ranges. And that means that you can then deform them slightly by changing their vorticity to make the travel time different. So you find a different steady state that's not isochronal nearby one of these. And then you can apply the Koch theorem. So conjecturally, you might, if something like this were proved and that stability condition were propagated for any isochronal flow, then it would imply that every Euler steady state is unstable in C1 alpha. Okay, then there's this issue of infinite time growth, so stronger than instability. And there's this nice conjecture by Udovich which is that a substantial set of inviscid incompressible flows have the property that the vorticity gradients grow without bound. At least this set is dense enough to provide loss of smoothness for an arbitrary disturbance of every steady flow. So it's sort of taking the Koch instability thing and saying that this should hold, in fact, for infinite time. It should have infinite time blow up, like the Nadarashvili example. And this is still open, so it's not known that you can do this around every steady flow. But with Tarek, we have some sort of result about the genericity of this type of behavior around certain steady flows, namely those which are Lyapunov stable, so like Arnold stable flows, and moreover have some structural condition that you have some strict monotonicity of the vorticity, say in a neighborhood of its maxima or minima. And in that case, you can actually show that the set of initial data nearby such a steady state with the property that you grow in C alpha, like T to the alpha, is open and dense in a ball around its steady state. So it's really a generic phenomenon in a neighborhood of these stable steady states. And an example of such a flow is Poisson flow, so just like a parabolic velocity profile in a periodic channel that satisfies this condition. But okay, you might hope again to prove Udovich's original statement, which doesn't require any structural property. And the way this proof works, I won't explain it in detail, is just that strict monotonicity of the vorticity in the neighborhood of its extrema give you stability of the flow map for all time. And that's crucial for capitalizing on this growth, to show this growth is sustained for all time. So in particular, because vorticity is transported and you have Lyapunov stability, if you have a region where the vorticity on each level is different, make a small perturbation of that, those levels can't move very far from where they started. Otherwise, they would violate Lyapunov stability. So the flow in the direction transverse to the levels of the steady state remains close to the flow of the steady state in that direction, which is, it doesn't move there. And you can use this then, so this is an all-time statement about the flow map. You can use this to say that the rotation of the flow in the direction around those levels stays close with epsilon, but it can grow like T. This, though, is enough to show the growth in C alpha. And here's a picture of something that the theorem applies to. It's an odd perturbation of the state on the torus, but it maintains, essentially it's Arnold stable on the box, and it's just a replica. And you can see the spiraling effect, which is causing growth like this. Okay, so for the remaining part of the talk, I want to discuss some aspects of what you actually see, the picture that emerges at infinite time. So not this sort of qualitative statement of small scale formation by saying that the C1 alpha norm blows up, but rather how do you describe the picture of what you see coarse grained? So ignoring the small scales. And like I said, the Udovich phase space is a very reasonable setting to talk about these, because you have a bound for all time in terms of the initial data of the L infinity norm of the vorticity, which in particular implies that as time goes to infinity on subsequences, you have weak star convergence of the vorticity to some profile. Of course, need not be unique, but depends on the subsequence. And if you form the omega limit set, so the weak limit, the collection of all weak limits of the at long time of the vorticity for a given initial data, then you could call the goal of understanding the long-term behavior as just studying the structure of this omega limit set. So there's some immediate points you can make about it. The first is that everything in this set has to have the same kinetic energy as the initial data did. And that's just because the kinetic energy, which is one derivative less than the vorticity, is weak star continuous. So all the weak limits share the same energy as the data. And that actually imposes pretty severe constraint on this. And in fact, it's really the only, I mean, aside from if you have other symmetries, it's the only really robust one we know. There's not an equality constraint, but another constraint imposed by certain Casimirs. So remember that any function of vorticity is preserved for any finite time. But these things are not weak star continuous. In fact, if you have a but what you can say is that if F is convex, then they're lower semi-continuous in the sense that the Casimir of the weak limit can be less or equal to the Casimir of the data. And this type of condition, say if F is just x squared, so this is the entropy, the L2 norm of the vorticity, it says that you can have some mixing at infinite time where the entropy is strictly decreasing due to some small scale filamentation and essentially averaging that's represented by thinking of the weak limit. And this is imposed also in this set. So you have to have these types of inequalities. Okay, there's a conjecture that I'll come back to at the end if I have time, which is that generically orbits of the Euler equation starting from a generic point in L infinity are not pre-compact in L2. So in particular, they should actually lose some entropy. They should have some mixing somewhere in the domain and lose some entropy at infinite time. Okay, and again, I'll mention this in connection with some other conjectures at the end. So what do we actually see in 2D? Well, because of the weak star continuity of the energy, and you have this equality constraint, and because you have this inequality relative to the data for the entropy, that imposes some strong information about how much energy can pile up in the weak limits. An argument that goes back to Fjortoft in the 50s shows that if you look at the energy sort of at wave number k, it can't be too large in the sense that if I take that wave number and send it really high to look at how much energy is piled up in the small scales, it has to go down at least like this rate in k. But actually what's seen in 2D is more than that. It's that energy is really cascading up from small scales to large scales. This is called the inverse cascade. And if you look, say, in experiments, then initially, if you start out with vortical structures that are small relative to the scale of the domain, over time, these things sort of merge and the late time behavior has vortices that occupy the largest scale that they can. So this is sort of what we should have in mind for what the long time behavior may look like. And some artistic examples from nature are like these large scale structures on planetary surfaces, Saturn's hexagon and Jupiter's spot. These are not really 2D Euler, of course, but they're essentially 2D motion, and these large scale features seem to emerge and last forever. This is the type of thing we want to understand. So we can begin by making some guesses about what happens, and we can see whether they're obviously right or wrong. The first is that mixing is just completely effective, and as time goes to infinity, the vorticity mixes to its average in the domain, which on the torus say is 0. That would say that the omega limit set of that initial data is just the average of the initial data, just as that singleton. This is obviously false because on the torus, like I said, it's mean 0. And so this would predict that the vorticity is mixing weakly to the 0 function, which has 0 energy, in particular energy that's not equal to the energy of the initial data. So that weak star continuity of the energy rules out this total mixing scenario immediately. The second conjecture is that, well, okay, it mixes as much as it can, but it's subject to this constraint that the energy is the same. And you could say, entropy seems like a good quantity to measure mixing, the L2 norm of the vorticity. So why don't I just minimize the entropy subject to this constraint of fixed energy? And if you do that, you show that the minimizers satisfy this equation, where lambda 1 is the first eigenvalue of the Laplacian. And so you recognize these are just the gravest modes on your domain, the largest scale eigenvalues on your domain. And so qualitatively, this looks kind of similar to that picture where you go to this large scale structure, but it makes a concrete prediction that you at least hover near the eigenspace of the first eigenvalue. And if the domain is a disk, say, and there's a unique one, then you converge to steady. And that's not typically what you see. We'll talk more about what you see later. And you could ask, well, okay, it's not what you see. Why? For one, this theory minimizes a very particular measure of the mixing, the entropy. And so what is sort of arbitrary? Why did you pick entropy as opposed to some other convex Casimir? That's one point. The other point is that there's really no reason why Euler should tend to necessarily minimize any of these things at long time. There could be other obstructions to really minimizing, and I think that's essentially why this is. But there are some areas of application of this this setup for Navier-Stokes at late times, so where you always keep some viscosity. So this theory, which is called selective decay, because it selects the entropy to minimize, is actually possibly governing end states of decaying Navier-Stokes at long time as you take viscosity small. So there is, anyway. Okay, so now I'm going to talk about a generalization of this idea that doesn't have the first objection of why did you pick entropy. It sort of systematizes any possible way that you could measure mixing. And this is a theory due to Schnellmann. So he defines what he calls mixing operators K as just these bistochastic kernels. So they're non-negative, they integrate to 1 in both directions. And K applied to F is just this integral operation. Examples of these bistochastic operators are composition with volume-preserving diffeomorphism, that's this delta function, or the pure mixing operator where you just set K equal to 1, that gives you the average. And I'll talk more about this in a second, but this set of all these mixing operators is convex, weakly compact semigroup of contractions. It's actually related to the closure of the orbit of the initial of some function in the group of area preserving diffeomorphisms. And it defines a partial order in the sense that we can say F is sort of less than G, or a mixing of G, if we can find a K in this set such that F is K applied to G. And we say that they're the same if when F is a mixing of G and G is also a mixing of F. So then, and that, yeah. So then Schnellmann introduced the set of all the vector fields U for which the vorticity corresponding to that vector field is a mixing of the vorticity of a given one, U0, which could be thought of as the initial data for Euler. And he intersects that set with equal energy. So he views this as a proxy for the omega limit set of the given initial data U0 for the Euler equation. And then he introduces a notion, vector field, which he calls a minimal element. And those are just the vector fields in this orbit such that if you have something else, which is a mixing of it, then they're the same in the sense I mentioned before. Then it is itself a mixing of the minimal one. So in a way, you could say these minimal elements are those for which the mixing is reversible. If I mix them with some mixing operator K, then I can find a potentially different mixing operator, which will sort of unmix it, bring you back. Okay, there's some reversibility here. Okay, and then what he proves is that first there exists a minimal element for any initial data in this set, and that any minimal element is a stationary solution of the Euler equations with the property that the vorticity is a single valued function of the stream and that functional relationship is monotonic. So in particular, they satisfy this equation that we started off discussing. And he characterized them as essentially, they're not quite Arnold stable, but essentially there's categories which are like Arnold stable: energy excessive, energy neutral, and energy deficient. That just means if you take that minimal element, this steady state for Euler, and you make any mixing of it, the energy excessive ones, any mixing will have lesser energy. Energy neutral will have the same, and energy deficient, any mixing will have more energy. And they roughly correspond to pictures like this, which are the two types of Arnold stability criteria, and the one sort of neutral one, Couette flow with with constant vorticity. Okay. So in a way, this theory is saying that if Euler is maximally mixing in any sense, doesn't matter what measure, entropy or otherwise you use to quantify it, if it's maximally mixing, this theory predicts that the long time limits are steady states or close to some set of steady states satisfying an equation like this. Again, let me just remark that this is not really observed to be true. So there's some gap between this prediction and what we observe. Now, in the remaining time, I'll just say with Michele Dolce, we've sort of revisited Schnirelmann's original paper, and we have the following perspective on it. So as I said, if it's related to this orbit and volume preserving group, so take the orbit corresponding to vorticity omega 0 to be just the collection of all vorticities which are reached by some volume preserving diffeomorphism in the component of the identity. And let's intersect that set with equal energy. It's clear that the Euler solution, starting from that omega 0, lies in this set for all time because of the transport nature of vorticity. And thus, if you look at the weak star closure of this set, it contains the omega limit set for Euler. Right? So moreover, because of the continuity of the energy, this is just the intersection of the closure of this one by itself with equal energy. Okay. So you could think of this set as a proxy for the omega limit set for Euler. It's probably much larger in most cases, but it contains all the information if you just take into account transport by divergence-free field and conservation of kinetic energy. And what we prove is that if you take any strictly convex function f and any initial vorticity which is bounded with some energy E0, then there exists at least one minimizer, which is also L infinity, of this problem. So you minimize over this proxy to the omega limit set of this measure of sort of mixing some convex function of, like you could think of entropy as an example. There always exists a minimizer to this problem. And moreover, minimizers are steady Euler flows that are minimal in the sense of Schnirelmann. So this sort of connects Schnirelmann's theory to the original selective decay theory that uses the entropy, but also it imposes this additional constraint that you're not just minimizing over any vorticity, which is say L2 or L infinity, but rather you have only those that can be reached by weak limits of these volume preserving diffeomorphisms. Okay, so probably I don't have much time to talk about the proof. I'll skip it. Let me just get to one, let me just emphasize, sorry, that what this is saying is that you cannot rule out convergence to equilibrium just from considerations of transport of vorticity and conservation of energy, which was also known from Schnirelmann's work, but this sort of makes it precise in terms of you can minimize different functionals and get steady states. And you can actually find multiple minimal flows on the orbit of some initial data. So you can't rule it out. But using these considerations, you can rule out convergence to certain types of equilibria. So let's say your domain has symmetry, like the two torus or the channel. Then you can say for any shear flow on that domain, you can find a point which is close to that shear in a suitable topology. So it's essentially a little bit less than the energy. These are vorticities. The energy would be h-1, so it's a little bit weaker than that. So you're close in that topology. But for those initial points, the set, this big set, the closure, if you intersect with constant energy and also momentum, since that's a new conservation law in these domains, this set contains no shear flows. So in particular, Euler can never damp to a shear flow if you start with this type of data. This guy's smooth, by the way. So what does this look like? It's just take your favorite shear flow, say Kolmogorov flow on the torus, and put some approximate point vortices in it. This will be a small perturbation at the level of, say, the stream function. It's a big perturbation for vorticity and for energy. And this theorem says this thing can never be stretched and go down to shear. And this is what you actually see. So depending on whether they're in flow of the same vorticity or opposite vorticity, you see that they actually never have tendency to go to shear. So in this case, they basically keep their structure due to the extra symmetry. In this case, they're sheared out, but you have these sort of cat's eye structures remaining forever. And it looks like you don't go to steady, but rather something with some time periodic structures that stay forever. How much time do I have left? Like 3 minutes or something?
Yeah, I think 3 minutes,
okay.
And then we take 2 minutes.
Okay, yeah. Okay, so it seems like even though, okay, there's this result that says you don't go to shear, on the other hand, there's a result that says there is a steady state in that big set that principle you could get to, you don't know. The numerical simulations seem to suggest that you never go to steady and that you always have some time dependence remaining. If you look at a more generic situation like random initial data and just wait long time, you see this robustly. So if there's no sort of structure to break the symmetries, you see that what you converge to is some wandering dipole pair. Typically, although not always, you could get some wandering tripole pair. And these things just rotate and move around the torus. So you never seem to go to a steady state in general, generically. However, notably, the situation at the end is much more simple than the situation at the beginning. And just by eye, you can see that there's some sort of decrease in entropy in a way, because you have this sort of typical element, and at the late stages, you have only some small collection of velocity fields or vorticity fields that seem to emerge. So a motivating question for all of this is, how do we understand this apparent decrease of entropy of the Euler dynamical system as a whole, if you look at these weak limits at infinite time, at least at the level of the phase portrait of the velocity field. And I make this remark because there's this alternative view of the fluid in configuration space for the Lagrangian trajectories, and there things can get arbitrarily complex. And maybe that's part of this picture. And so I'll end the talk with these two conjectures that lend some rational explanation to this decrease of entropy. The first is the one that I mentioned by Schwerak, which is that generic data give rise to orbits which are mixing, which are not pre-compact in L2. The second is one due to Schnellman, a slightly later paper than the one I mentioned, where he says that for any initial data in L infinity, the collection of all weak star limits of the Euler orbit that omega limit set consists of vorticities that themselves generate an L2 compact orbit. So in particular, it consists of things like steady states, periodic motion, quasi-periodic motion, but things for which if you start Euler with them, you don't mix anymore at infinite time. So you mix to get to them, but you don't mix after if you started with them. And so if you put these two things together, it gives this picture of entropy decrease, since the generic points are not like that, but the things that you sort of weakly converge to are like that. So finite times you map the ball in L infinity to itself, but then the omega limit set, the collection or the union of the omega limit sets of each point in the ball, may be some much smaller sparse set. And this would represent things like these large scale states. And two things in support of this conjecture. First, in his lecture note, Schwarak proves that for any initial vorticity, this set, the omega limit set, contains at least one L2 compact orbit for Euler. So they are there. And so the conjecture of Schnellmann is just that everything in here is that. And also, there's a certain sense in which both of these conjectures are true to the Inviscid damping results in neighborhoods of shear flows. Of course, the genericity in the topology is not the same, but open neighborhoods in some Chevret topology of some steady shear flows that are suitably stable have the property that either they weakly converge to a shear or they themselves are a shear. So in that whole neighborhood in phase space qualitatively behaves like this. Okay, so that's it. Thank you.
Thanks a lot. So we have some time for questions. So any questions, so you can
I have a quick question, Theo. Beautiful talk. Yeah. So many people, including myself, use the Jupiter spot as sort of as an example of this. But in fact, this is in a rotating frame, right, on a sphere. So is any of this, can any of this be generalized to something like a flow in a sphere or something like that?
Yeah, definitely. The simplest setting to generalize to is the beta plane equations on the T torus. And I think, of course, that introduces an anisotropy that allows the existence of stable steady states and these minimal flows and things. All that can be generalized to that setting. And also you could study the rotating sphere itself. I mean, there's just, a little harder technically in the sphere, but you could. Yeah.
Thank you.
Any more questions, Peter?
I had this question about the omega limit set. What do we know about this? I know that in Schneermann's theory, but I'm talking about the actual Euler. What do we know about reversibility, time reversibility there?
Well, in a way, you know that there's some time. So I view this theorem of Schwarak as some quantification of time irreversibility because it says that there, for some, well, both of these are some measure of time irreversibility because you're converging in both of these cases to something which has no mixing. If you were to start with it and run to infinite time, so you
I understand. I understand. Once you are there, then at the limit, in particular in the case, and we end up with a shear and so forth, you're in a smooth case that's time reversible. I'm asking globally because that's, I think it's very much related to the picture that you are drawing. So if we are to end up having a simplifying picture, the simplest way to think about it is that it is going to be time reversible globally.
Yeah, no, I agree.
So there are no clear. Yeah, so in Schneermann, it is time reversible in the original definitions, right? But it's not
sort of reversible. Yeah, that's right. Yeah, so let me actually
minimality is reversible. Minimality means reversible.
Right. Let me remark that, in fact, I think it's an open question to even say that if you union the omega limit sets of everything in this ball, that it's not the whole ball. So a natural place to start, in my view, is this wandering point of Nadarashvili. You want to just say that state, which is somewhere in here, cannot arise as a weak limit of some other thing, and I think that's true. But I don't think there's any proof of that type of statement to really quantify irreversibility. Yeah.
Okay, so I see one more raised hand. Unless Peter, you have any other comments on? We're good. So we've now Milo Viviani.
Hi.
So just
Hi, Theodore. Thank you for the very nice talk. I just wanted to ask, how did you get to the picture where on the torus, where in the final state you had like these two patches of three small vortices? In some of the slides, you showed like these two possible. Yeah, exactly. Yeah, exactly. Like the second one, I've never seen this kind of final
so
state.
like 2 summers ago, I just ran a bunch of random initial data, and most of them look like this. One of them looked like this. That's it.
And they never merged after that.
No,
so they just continued to move.
Yeah, it seems to be some quasi-periodic. So these guys rotate like solid body rotation of the three, kind of like point vortices, and they themselves almost move like a dipole pair. It would be really interesting to construct a solution, even a point vortex solution on the torus with this property. I don't know if that is known to exist, but it didn't appear that there was any tendency of these things to destabilize and merge.
That's very
the video's on YouTube, by the way. So
okay.
You can like and subscribe.
Yeah, I will. Thank you. Thank you very much.
Yeah.
So I think Anna has another.
Yes, I have a question, comment, follow up from Peter's question also. What type of numerics did you do to get these pictures? Because what I'm thinking is that one should think of many of these pictures, at least in turbulence, as really slightly viscous fluids.
Yeah.
And so those will be time irreversible.
Yeah, so you're right. So I mean, these are actually Navier-Stokes simulations with very small viscosity. So what I do is I check that the energy roughly is the same from beginning to end. So the energy almost doesn't change. Entropy drops a lot because what Navier-Stokes does is it just merges these filaments. But one could hope that in looking at these pictures, it's somehow like looking at coarse graining of long-time Euler. But of course, there's a leap of faith there. Let me say that the numerical code is due to Navid Constantino. It's publicly available. You can get it on GitHub. It's very easy to run on your own computer. I run these on my laptop and it takes a couple of hours. And it's a pseudospectral code. It's pretty good code, but yeah.
Can I ask a question?
Camilla?
Yes, Theo, I wanted to ask you, so this is a qualitative picture, and I wanted to ask you if you can actually extract some quantitative estimates a la coarsening type of estimates. I'm thinking about some specific work of Felix Otto in these directions. So for example, monitoring, I don't know, some inverse sublet norm of the vorticity, things like this.
Well, aside from what's done in the Inviscid damping sort of program, I don't think much is known. So there are these like quantitative estimates of growth in some strong topologies like C1 alpha or whatever. But in terms of mixing and things like that, only or even loss of compactness in general, the only examples I know of that are through the whole Inviscid damping program. So there's no even like sort of soft argument to prove that loss of compactness, as far as I know. So no, I would say it's kind of a sorry state from that point of view.
Okay, thanks.
Thank you very much. So we thank Theodore again. And I would try to keep the schedule. So we move immediately to Franziska Weber, the last speaker for today. So I just wanted to introduce Franziska Weber from Carnegie Mellon University. And she's talking about sufficient condition for flux scaling laws in the stochastic Navier-Stokes equations. So please.
Thanks, Gianluca, for the introduction. And thank you very much for inviting me. It's a pity we're all remote, but at least we get to see each other. So that's something positive. And yeah, I think for you guys, it's evening, so I try not to keep you too long, but who knows. So this is a joint work with Jacob Bedrosian, Michele Dolce, and Sam Ponchard-Smith. I think some of them are actually here. They can correct me if I say something weird. And so, I mean, the problem is like there's not really much mathematical theory for turbulence, but the engineers need it every day for their simulations and so on. And so what we thought is we wanted to try to understand what was there a little better. And we started with the theory by Kolmogorov, also known as K41. So he wrote 3 papers in 1941. And that's, I guess, part of our mathematical turbulence theory. And so we tried to understand this, and then we had the idea to try to make one of his results, the so-called 4/5 law, mathematically more rigorous, and that's mostly what I'm going to talk about, and some 2D versions of this. Yeah, we will, it's not completely rigorous, there will still be an assumption, therefore it's called sufficient conditions, and you'll see it soon. And so the model we use is the stochastic Navier-Stokes equations. And the reason we chose that is, on one hand, Navier-Stokes equations are kind of the canonical model to study turbulence. And then also it's maybe close to the setting by Kolmogorov. So he considered statistically stationary flow, and for stochastic Navier-Stokes equations, there is indeed stationary solutions, as we will see. We'll see. Okay, so here U is the velocity field, as usual. P is the pressure, and U is the viscosity, the inverse of the Reynolds number. And we consider this on the torus in R3, and then W is an additive forcing. It's a wide in time, colored in space Gaussian process. And so here beta K are independent one-dimensional Brownian motions. EK are the orthonormal eigenfunctions of the Stokes operator, and sigma K are fixed constants, and they satisfy this condition here. The epsilon will show up later as the forcing input again. And so this may be generalized to more complicated types of noise. We didn't try that, but yeah, it may very well be possible. And so if you just look at these equations and don't worry too much about the smoothness and do some formal manipulations, you will see that there's lots of symmetries in these equations, and these are here. So this is on R3. Some of these also hold on the torus. You can tell which ones won't. And so if you have a solution U of the Navier-Stokes equations and you translate it in space by some vector Z, then this will again be a solution, assuming the noise has the same property and like ignoring the initial condition. Similarly, if you translate in time by some tau real number, then you will again obtain a solution of the equations. You can also do Galilean transforms, which is this type of transformation here. Here U0 is a vector in R3, and you translate the spatial variables and add this U0. Furthermore, you can reflect the solution in space. You can do rotations with R matrices in SO3. This one doesn't really work on the torus. And you can rescale the solution for some lambda in R, and S equal to -1. This will again be a solution. However, so this is all formal calculations. And when you look at real flow, it doesn't look like it's always satisfied. So this picture here is an experiment of a flow in a wind tunnel. So you have some nice laminar flow coming in, then it goes through a grid. You have some transient region and then a turbulent region. And now in this turbulent region, and even here, it doesn't look like there's much symmetry at all. So this is a picture from the book by Frisch, by the way. And so then you wonder, okay, maybe the problem is that these calculations were all formal, or maybe the model is wrong. It would turn out it's slightly different. So what you can also do, you can quantify this in some way. So you can put like a hot wire probe somewhere in this wind tunnel, say here, and measure the velocity fields you obtain over time. And this is what the picture looks like if you do that. And so this is normalized to have 0 average velocity. And we see that it looks quite irregular. It looks like some stochastic process, and maybe not too regular. And then also say we had this symmetry that you can translate in time, and then you should get a solution again. And if you translate in time, say you do this experiment again a little later, it still looks very irregular, and maybe qualitatively kind of similar, but quantitatively, if you compare a certain point, say around here, then in this picture, here they're actually relatively similar, but they're very, very different overall. And so I guess people wondered about this phenomena, and Kolmogorov and others realized that, okay, maybe this is not the right approach to take, but instead maybe one should look at averages over time, or repeat this experiment many times and see what you get on average. So that's what's done in the next picture. So here you measured what kind of velocity fields you get, and you do some binning, measure how many times each of them appears. And this is the picture you get, some kind of histogram. And you see, we get like some sort of, it looks like a Gaussian curve, so maybe there's some relation to the stochastic process. But it looks much more regular than before. And similarly, if you can repeat this experiment a little later, that's what they did a few minutes later, you get kind of the same picture. And even like when you look at, okay, where is about the maximum is maybe around 800 events. This one is the most commonly observed, around 48 or so, minus around 10 and 80 are the tails. And the previous picture, it's kind of similar. So Kolmogorov and I think others before him, Taylor and so on, realized this and thought maybe what is needed is some kind of probabilistic description of turbulence and interpreting everything in a probabilistic sense. And so based on, like, he observed the experiments and the flow, and then made hypotheses based on that. And then based on these hypotheses, he derived further relations. And so what he noticed is that at high Reynolds numbers, when the viscosity is very small, the symmetries of the Navier-Stokes equation seem to be restored in some statistical sense. So he noticed that the flow is sort of statistically stationary, which corresponds to the time translations. So the distribution of u at time t plus tau is the same as the one of u at time t. And similarly, he defined statistical versions of the space translates and the rotation invariance. And so he did this, okay, you can do this in a global way as well, but he did it in a local way because of boundaries and so on. He realized it cannot be globally restored. So he defined what is called a velocity increment, or which is just u at a spatial point x plus h minus u at x for some vector h in R3. And the h should be reasonably small in norm. And then as long as y is also small in norm, the increment of u at x plus h is distributed in the same way as the increment at x. And similarly, if h is small, you can rotate the increment and it should have the same law as u, the increment of u. And then based on that, he also made these two hypotheses of similarity. So if the flow is locally homogeneous and isotropic, so it satisfies these two properties, and the Reynolds number is small, then large, then the laws of the increment are uniquely defined by nu and the mean energy dissipation rate epsilon. In his case, I think he looked at freely decaying turbulence, so it was related to this quantity here. Then he had another hypothesis, and this was when nu is basically very small, and so h is large compared to nu. And to do this, he defined what was called the Kolmogorov scale, which is this quantity here. So it's nu to the power 3/4, and then epsilon, the mean energy dissipation rate, to the power minus 1/4. And as long as the mod of h is large in comparison to this Kolmogorov scale, then he said the laws of the velocity increments are uniquely defined by the mean energy dissipation rate, and they do not depend on the viscosity. However, since then, people have done lots of experiments and realized that this second hypothesis, it may not actually be true. So it's debated. I mean, there's various arguments for or against it. Here's one of them. So one of them is that it would lead to scale invariance, which is this property here. So assuming it's independent of the viscosity, then what you should get is that the increment of u along lambda h is distributed in the same way as the increment of order h times lambda to some power s for some s in the real positive numbers for any h that are sufficiently large compared to the Kolmogorov scale. So what this would mean is that if you look at the say expected value or the average of some sort of the increment, then it should be distributed in this way. There should be some universal constant Cn, and then the mean energy dissipation rate, and then the size of the increment to the power n divided by 3. and Cn should be some universal constant. However, physical experiments indicate that the Cn may not be universal, and this is what is called intermittency correction. So these are various theories in order to make this still work. And actually, I think Kolmogorov himself in the 1960s realized that it may not be true, and I think he made this constant probabilistic, if I remember correctly. And so the problem with these theories is it's mostly based on empirical considerations, and it doesn't seem like one can directly refer them from the fluid dynamics equations. So instead, it seems like what one looks at is like some experiments and do some interpolation of the curves. And so this may be related to higher order regularity or smoothness of the solution. And so here's a picture to try to illustrate this. So what they looked at is this exponent here and compare it to n, so the exponent here. And so, okay, so this was what it is. So for different n, and this would be the exponent, it's called zeta n. So in Kolmogorov's theory, it would be zeta n would be n divided by 3. So this is this line going through 0 here. And then the dots here in these plots are different experiments by different people. And we see that they, except for this area here, where they seem to match quite well, they deviate quite a bit around here. And so the other, the dashed line and the solid line here are two intermittency corrections. I think one is called the beta model and the other one is called the LN model. There's like different parameters. And we see they also, I mean, maybe this line matches a little better, but there's still quite some deviation to some experiments. And so maybe, okay, you can argue maybe there's some inaccuracy in the experiments, or it's not really, the viscosity wasn't really small enough, and there's other arguments for that. And people have investigated this, but I think there's no one theory that is widely accepted. So one thing, however, that looks like there's some agreement between these theories is like this area here. And in particular, the point where n is equal to 3 and zeta is equal to 1, which there's various experiments that seem to match them and all the theories. I think the theories, though, they were kind of correlated to this. And so this would be yeah, n equal to 1. So you see in the Kolmogorov, through Kolmogorov's theory, you would get 1 here. And so this is related to what is called the 4/5 law. And because there's so much agreement from the experiments, there is some hope that one can actually rigorously justify this and derive it based on the fluid dynamics equations. And it should also be independent of the intermittency corrections. And so that's what, and it's also the second hypothesis of similarity should not be needed for this. So that's what we try to do. And here's an informal description of the 4/5 law. I think we saw it earlier in this conference already. So we take the increment of u in the direction of the increment vector to the power 3. So, okay, so this is scalar, so we can do that. And then the expected value of some average of it, depending on what type of flow you consider or what type of solutions. And then this should be for h between some dissipation scale, let's call it LD, and an integral scale Li. This quantity should behave more or less as minus 4/5 epsilon times the mod of h. And so that's where the name 4/5 law comes from this constant here. That's maybe a little arbitrary. And okay, and then so this is true in some between some scales, and so you would get some error terms here, depending on how close h is to one or the other. So in Kolmogorov's theory, the dissipation scale was of this order, so nu to the 3/4, and the integral scale is related to the input through forcing, or I guess maybe the time you wait. And so basically what this may heuristically mean is it's some sort of balance between the dissipation due to the nonlinear effects, so the energy flux, and with the energy input. So epsilon for us is the sum of the constant sigma, okay? So it's related to the input through the forcing. So the framework we look at will be martingale solutions. And so as I said, we picked this model because you can actually show existence of solutions and stationary solutions. And so basically what they are some people here are expert on them, so I don't need to tell them. Sort of a stochastic equivalent of the Leray-Hopf-weak solutions. And what you need is a stochastic basis. Omega is a probability space, Ft is a filtration, and P is a probability measure, and the beta K are Brownian motions. And then you have a stochastic process U, depending on time and probability space, taking values in L2 diff, by which I mean the L2 functions which are divergence free. Then the sample paths of U are in this space, so basically they have the same regularity as the solutions of the deterministic Navier-Stokes equations under some conditions of on the forcing. And then for almost every omega in the probability space, U of omega is a weak solution of the stochastic Navier-Stokes equation. So you look at this in a weak sense. And what you have in addition is an energy inequality, some average energy inequality. So for almost every times T2 larger than T1, the difference of the expectation of the L2 norm of U at time T2 minus the L2 norm at time T1 plus the expectation of what you get from the dissipation is bounded by what you get from the forcing using Ito's formula. So the epsilon times the difference of times. So epsilon was the energy input. And Bensusa and Temam have shown that such solutions exist. And what is more, there's also statistically stationary solutions. Kolmogorov, as I said, considered statistically stationary flows. So it's good to have a result on these. This was done by Flonderly and Gatterek in 1995. And so basically what it means is everything's the same as before, except that the paths of U at time t plus tau have the same distribution at the same law as the paths at time U. So when you go back in this energy inequality from before, then this term and this term will be the same. And so your energy inequality will only involve this term here. And so that's what you get as a stationary energy inequality. And you see that, okay, so using Poincare inequality, you still get a bound on U from this, but it will not be uniform in U anymore. And so that's going to be our main problem and where we need an assumption. In addition, if you have homogeneous forcing, one can show there's also homogeneous stationary solutions on the torus. I think that was done by Romito. But instead, you can also take spatial averages. So that's basically equivalent. So now let's go to the condition that I mentioned that we will need. And so it may have bothered you that we have this inequality here instead of an energy balance. And so, however, we don't need this for proving for Fifth's law, or I don't know, maybe there's another way that needs it that I don't know. And so the thing is that if you look at the stochastic heat equation, then you will actually get this energy balance, but there's no energy cascade and there's no nonlinear effect or so. So this may not actually be related to the nonlinear effects or say anything about that you need to derive the 4/5 law. As I said, if you use Poincare's inequality, you get that this quantity, so the expected value of the L2 norm of U is bounded by some constant depending on the domain times the expected value of the L2 norm of the gradient, which from the energy inequality is bounded by some constant. And so what we now call weak anomalous dissipation is if this quantity over here goes to 0 as nu goes to 0. So if you had like not stationary solution, it would make sense that this goes to 0 because you have a bound on the energy of U, but because we have stationary solutions, we don't actually know. So we have to make this assumption. And what it says is maybe that like energy in the low frequencies get transferred to the higher frequencies. And so there has been actually some progress to prove this, not in this exact setting, but on one hand, it has been shown that for the passive scalar equation, this equation here, if V is weakly mixing, then it satisfies the solution satisfies the weak anomalous dissipation condition. This was done by Bedrosian, Cotticellotti, and Glatt-Holz in 2016. And also more recently, if U is if the velocity field V here is either coming from the stochastic 2D Navier-Stokes equations or hyperviscous 3D Navier-Stokes equations, and I think also for Galerkin translations of the 3D Navier-Stokes equations, then F also satisfies the weak anomalous dissipation condition. This was done in a recent work by Bedrosian, Alex Blumenthal, and Sam Punch-Smith. Okay, so let's see what we prove based on this condition. So again, let's take the velocity increment from before, and now let's define some averaged version of what we had earlier, the cubic the cubic expression in the structure in the increment, and we call this the longitudinal structure function. So what we do is we take again the increment in direction n hat and dotted with n hat to the power 3, and now we take averages over the sphere. So that's the factor 1 over 4p. Take the integral, and then we also take averages over the torus and the expected value. So before we did not have these two averages, and then this quantity here divided by L basically behaves as -4/5 of epsilon as we send the dissipation and the integral scale to 0, which is what this theorem here says, more or less. So assuming the weak anomalous dissipation condition, and we have a sequence of solutions, then we have a dissipation scale LD depending on nu that goes to 0 as nu goes to 0, and an integral scale, and then if we take the supremum of L between these two scales and send nu and the integral scale to 0, then this will be equal to 0. So basically this is equal to -4/5 epsilon plus some error terms in these two expressions. So the only assumption that we need is the weak anomalous dissipation condition, as I said. Otherwise, one can just work with the regularity of statistically stationary solutions of the Navier-Stokes equations and the regularity you get from these. And also the energy balance is not needed. Inequalities is good enough. And yeah, and then yeah, I guess if you assume symmetries and so on, then you can define a version without the averaging. And so let me talk a little bit about those integral and dissipation scales. So Li just depends on the continuity of the covariance matrix of W, so the noise, and so depending on how regular that is, it will be larger or smaller. And you'll see this in the proof in a moment. So the dissipation scale, we needed to satisfy this inequality. It has to be strictly larger than nu to the square root of nu times the expectation of u to the 1/2. So here's where you can see the weak anomalous dissipation condition. This only goes to 0 if we have this condition, square root of epsilon, the energy input. So now this is related to Taylor's macro scale, which was this quantity. However, if you remember, the Kolmogorov dissipation scale was of this order, so it's quite a bit smaller. It's actually nu to the 3/4, and we don't know how to modify the proof to actually get it to be that small. So this we didn't manage. Now, if you assume symmetry, so if you assume a homogeneity or isotropy or a local version of this, one can show the same result without taking the averages from before. The homogeneity, as I mentioned before, one can prove that there's homogeneous solutions for the isotropy. I don't think that is known, and it may not be possible. Now, the proof ideas are borrowed from Frisch, the book by Frisch from 1995. We do need a relation, as I'll show you in a moment, that Monin and Yaglom described. Then there's also some ideas we use from Eying and Ni and Tanvir. I guess what you can say is ours is for the stochastic Navier-Stokes equations, and everything is mathematically rigorous besides also mathematically formulated assumption. And then what I also want to mention is that Theo Rivas proved the Lagrangian version of the 4/5 law in 2018. So if you go to Lagrangian coordinates. Now, in order to prove the 4/5 law, we use what is called the 4/3 law, which is some similar relation that is maybe a little less messy to prove. So I will show you the proof of this, and then the proof of the 4/5 law is actually very similar, like the same ideas, and you will need this result in addition. So what it is instead you look at this other structure function. So before we had just the increment in the direction of the increment to the power 3. So what you do now is we take the increment in the direction of the increment vector, and then we take the mod of the increment squared. I'll call this S0. Now, this quantity behaves, who would have guessed that, as -4/3 of epsilon, and therefore the name 4/3 law. Otherwise, everything's the same. You have it's the same scales and so on that you use. And okay, so let's have a little look at the proof. So in order to prove it, we need what is called a Karman-Howard-Monod relation. So I think Karman and Howard were the first one to come up with a relation of this form. They did it under the assumption of isotropy in 1938, and then Monod later generalized it in 1965 to non-isotropic flows, and therefore the name, the long name. And so basically what it says, okay, what you, these too many formulas here, what it says is it's a relation on the time evolution of the second order correlations. So the expected value of the average of U tensor product with U at x plus h in space, and how it relates to the energy flux, which is basically this quantity, if you rewrite it, and the input for the forcing, which is this term here that you obtain after using Ito's formula. So the rigorous or the version we use here looks like this, which looks a little messy. So here eta is a test function that is isotropic and smooth and compactly supported. So here phi and phi are radially symmetric and smooth test functions. And then we take the first one with the identity matrix, 3x3 matrix, and this one is a vector, the direction of the vector tensor product with itself. And so if you contract the correlation with this test function, and you take the difference at different times, so this looks a bit like a time derivative, then it's equal to the forcing term. It's coming from the forcing term, and that's coming from the flux, and then this term here is coming from the dissipation. So you wonder where the pressure went, and the pressure disappeared because of the test function being isotropic. And so formally you get it by computing an equation for U tensor U with t x plus h, and then using Ito's formula. And to make it rigorous, you first mollify the equations, and then do all the manipulations with the modified quantities, which are now smooth. And then you pass the modification to the limit to 0, and after integrating and everything against test functions, and then you just need to use the regularity that you have from the equation and the integrability in order to obtain this here. So it's not that hard. Now, if you have statistically stationary solutions, then these two terms will be the same. So it vanishes, and what you get is some relation between the forcing input, this relates to the energy flux, and the dissipation. And okay, so that's this expression here. And now, in order to get the 4/5 law or the 4/3 law, you use specific test functions. So for the 4/3 law, you set the second term here equal to 0. And for the 4/5 law, you set this term here equal to 0. So let's do the 4/3 law because it will be less complicated. So we take this test function, plug it into this expression here, and then we change to radial. And so what we'll get is some spherical averages of these quantities here. These are already spherically symmetric. Okay, and so that's what we would get after doing some computations. So this term here, which looks kind of like some structure function, becomes S0 multiplied with L squared and the derivative of phi, and then the other terms become this expression. So these two are averaged versions of the second order correlation, and this term here is from the forcing. And so this is what basically an OD in the sense of distribution, and so you can rewrite it in this form. The derivative of in L of this quantity is equal to that stuff over here. So you integrate it in L and then make sure that the lower boundary term here vanishes, which it does. And so you get this expression after dividing by L to the 3. And so now we see on the left-hand side, we have what we would like to have. And then on the right-hand side, we have to show that this thing here is approximately minus 4/3 of epsilon. And so you look at the different terms. So this one coming from the covariance, we rewrite it as 4/3 average of A, and this is actually epsilon if you make the computation, plus some error term. Now here we see that this thing is small as long as L is small and A bar is continuous. And so then this term goes to 0. So here is where you need the integral scale. Then for the other term, you use basically Cauchy-Schwarz inequality. And then, so this was the second order correlations and derivatives of it. So you get that this is basically the expected value of the gradient of U in L2, square root of it, and then the expected value of U, square root of it, and times nu divided by L. Now, if you use the energy inequality, then square root of nu times this term is bounded by square root of epsilon. That's where you get epsilon from. And here you have square root of nu. And now you see this looks suspiciously like the Wick-Galamos dissipation condition. So you use that, and then you'll get that this goes to 0, as long as you choose the dissipation scale in a good way. So what you have to choose it like is this form. So this term here has to be little o of the dissipation scale, and then this goes to 0. And so what you end up with is 4/3 of A bar, which is epsilon plus the error terms. And then the 4/5 law, you use that, you have the 4/3 law, and then you do basically similar calculations that are just a little more messy because you have different, the tensors are a little more intricate. And yeah, so if you don't assume anything on the solution, you can also derive this kind of inequality. So if you don't use the 4/5 law, which I don't know if it has any value, so these average structure functions also satisfy in the limit that they're between -8/3 epsilon and 0. However, this doesn't tell you anything about regularity because these are not signed quantities, and you have this 0 here, and not like if you had something strictly less than 0, then maybe it would mean something. However, if you assume the energy balance, you can also derive some necessary conditions. So assuming you have an energy balance for you, and say if we just assume the inequality before, and you have some sort of regularity. So instead of so this would be what you get from the energy balance as long as S is equal to 1. So if you assume it's a little larger than 1, then you get that both these structure functions will go to 0. So there's no 4/5 law in this case. On the other hand, if you assume the energy balance and that you have some sort of 4/5 law, so this is just the opposite of the previous one, then for S larger than 5/4, this quantity goes to infinity. So again, if S is equal to 1, then it's bounded, but if it's like larger, then it goes to infinity. So you have some kind of irregularity. Okay, so now set Flock scaling law. So let's look a little bit about 2D. So you wonder, okay, why should we look at 2D Flock scaling law since the world is 3D? On one hand, there's maybe more results in 2D. There's more regularity, so it may be easier to prove things like the conditions, the Wick-Galamos dissipation condition. And on the other hand, it may be interesting by itself because there's some phenomena, like for example, what I'm picturing here, weather, where you have some sort of 2D phenomena. And then also, so the general physical picture is that in 3D you get all these formation of little small eddies. So the energy goes from the large scales to the smaller scales, whereas in 2D it seems to be the opposite. You may have some small perturbation and you get like some large vortices like this hurricane here. And so that is related to possible appearance of an inverse cascade. So some scaling law for large scales L, and that apparently also appears in other phenomena like in MHD or plasma turbulence and wave turbulence. So it may be interesting to study that too. So in 3D has been studied a lot by in experiments and so on, but in 2D it's a little less. There's a little less literature and it's harder to do physical experiments, obviously. But there's still some results by people like Bernard Lindborg or Batchelor or Jacob, who looked at structure functions, and then also Krajnon and Fjordhoft extensively studied 2D turbulence. So the model we look at in this case looks slightly different, still very similar. So we add some damping of the low modes here. Otherwise, it's the same. We have a Brownian motion. What's also different is instead of looking at unit length torus, we look at a torus with side length lambda, where we send lambda to infinity in the end. And the reason we do this is in order to find scaling laws for the large scales, otherwise you couldn't do that. An alternative point of view would be to take the whole space instead, or yeah, a sphere, and do it on that. We chose this. This was, I guess, easiest for us. And yeah, so what you need is this damping term in addition. And what you also, like, instead of having the Wiener process from before, we make it slightly more general of this form. Again, beta k are one-dimensional Brownian motions, and gk lambda are smooth, mean zero, divergence-free functions. And so if you just chose what we had before, then it wouldn't work out so well with changing side length torus. So you need some additional technical assumptions on gk, but they are not very strict. In vorticity form, the equations look like this. We have seen this before. So now we have the curl of the noise term, and we let epsilon is again from the coloring condition before, the same, the input for forcing, and now eta is the forcing in the vorticity form of the equations. Make some assumptions again. So on one hand, we assume an energy balance for stationary solutions. So here it's 2D, so we have more regularity, so it makes sense to assume that. And so for the velocity field, it looks like this. So this is the term coming from the damping. So here lambda is to denote the L2 norm on the torus with side length lambda. And then we also have an entropy balance, which looks like this. So here eta is the other term from before, so this term here. Now we say, so weak anomalous dissipation is now this condition, which are kind of two conditions. So on one hand, we again, for the entropy, we need some anomalous dissipation. And then we also need that this term here coming from the damping goes to zero, as we send alpha to zero, uniformly taking the supremum over nu. So if you relate alpha and nu in some way, say you set them to be of the same order, then you can remove these two supremums here. And okay, so now, as I mentioned earlier, what you get is a dual cascade. So on one hand, you get a direct cascade for the vorticity, which looks like this, and then you get an inverse cascade for the velocity. So this is also called Yaglom's law. So here we take it looks, I guess, related to the four-thirds law from before. So you take the expected value of some average of the increment of the vorticity, and then the longitudinal increment of the velocity, and that scales as -2 eta, which is the forcing input in the vorticity equation times the mod of h. You can also derive something for the velocity field, some sort of what was the 4/5 law before, now becomes this expression we see here, h is to the power 3. On the other hand, so this was for small scales, the dissipation scale and an integral scale, and now if the scale is much larger than the integral scale, so the scale of the forcing, and some, let's call it damping scale, L alpha, then the third order structure function of the velocity field behaves as 3/2 epsilon and then the mod of h. So here the sign is switched. Yeah, that corresponds to the direction, I guess, of where the energy goes. And so I get something in the chat. Oh, okay. Thanks. Or maybe I had a question. All right, so let's I'll be done soon. Let's make this more rigorous. So the first one, as I said, is called Yaglom's law, and here's the rigorous version of it. So I said we send lambda to infinity, so it must be a continuous monotone decreasing function in alpha since alpha goes to 0. And assume we have this weak anomalous dissipation condition, then this expression here, which is, okay, the averaged version over the torus and the sphere of, or the circle now of this expression, this is the informal version, it behaves as -2 times eta. And so what you need is, again, that the dissipation scale goes to 0 in this way, and then the integral scale depends on the forcing the covariance. On the other hand, for the inverse cascade, this is what you get. So you get that, okay, for the sending the integral scale to infinity, then in a range of scales between the integral scale and the damping scale, we call this the damping scale, again, lambda goes to infinity, then these two, this is kind of the related to the 4/3 law, the structure function S0, and this is the longitudinal structure function behave like 2 epsilon or 3/2 epsilon. And so here we need the condition on the damping that this is basically going to 0 with the, or is smaller than the dissipation scale. Yeah, and the proof ideas are again kind of similar, but you have to mess around a little more with some higher order tensors. And I guess the harder part was to figure out what one has to prove and what the correct model is. And so here are some references. So the 3 papers by Kolmogorov, of course, from 1941 that I was referring to. And these 2 papers by Bernard and Lindborg are related to 2-dimensional turbulence and structure functions. And then these are the papers that I explained just now. And then I mentioned that Jacob and Sam and Alex have managed to prove the weak anomalous dissipation condition in some settings, which is in this paper. And then they actually proved something better in this paper about the bachelor spectrum of scalar turbulence, basically the energy spectrum. And yet, thank you for your attention. Thanks for being with me so late in the evening in Europe.
Thanks a lot. And, is there any questions from the audience?
Everyone's tired.
Yeah, so we Europeans at least.
Sorry.
The audience. Okay, so I think we thank you again, Franziska.
Thank you.
And so we are done for today's session.